I'm going to name names in this one. Very seriously at the end. Maybe some people will be shocked. Steven Weinberg. So let's see what Feynman says. All the stuff that Susskind talks about. So then the question is, why am I talking about this?
Mm-hmm.
And the answer is because I understand it. And the people I'm going to be calling out on the other end don't understand it. And that's had very bad and continues to have, I think, very bad consequences for the practice of physics.
In our last conversation on Einstein's theory of special relativity, I suggested that we start with some context, some historical context, but you took the reins and that episode went amazingly. And this time on Einstein's theory of general relativity, it should already be clear, at least to our watchers rather than our listeners, that you have done a tremendous amount of preparation for this one. So I thought I should just start by saying, where do you want to begin, Tim?
Good. So let me, yeah, I did a lot of preparation for this because in the last one, I ended up waving my hands around in the air a lot and trying to remember quotes that I couldn't quite remember. And this one, I want everything to be right. People can understand it. I mean, the nice thing is
general relativity
and special relativity. So just so people know, it would be a good idea to watch the first one on special relativity first. But I'm going to spend a lot of time first with special relativity, making some points about it, and then doing some concrete examples, which I think you'll like.
Yeah, that'll be great.
And then once we're clear about that, then we can move on to general relativity. I should say we spent a lot of time doing history. In the first one, I wasn't kind of expecting to, but we did. And it's not going to be the case for general relativity. The main reason is there's a really interesting history there that I don't know well enough. In terms of, you've got 10 years between special relativity and general relativity. I have a quote here from Einstein about that 10 years, but the actual story, the historical story of getting to the general relativistic field equations is amazingly exciting. There's a breakneck race at the end between Einstein and Hilbert to get to these equations, and you have to know how efficient the German postal system was. They're sending postcards back and forth. But this is not any stuff. This is just what I've learned from sitting in hearing other people talk. So I'm not going to try to do that. And there are some things, I don't know if I even promised in the last time I'd tell you why people mistakenly think that the Michelson-Morley experiment was so important, which I never got to. I looked at it and said, I never told you that. I can tell you that if you want. I don't know if you care about that. But what I want to do is really very carefully, again, this is all highly, highly conceptual. Not in the math. Insofar as there's mathematics, it's geometry. And insofar as there's geometry, it's visualizable.
Amazing.
And some people like me are visual, right? I work with pictures in my head. Some people are more algebraic, right? They like calculating. But if the subject matter is geometry, go back and do it the way Euclid did it, right? You don't have equations. You're not solving things in that sense. You're constructing things, and you think about how that works. And this really is the way to understand both of the theories of relativity, I think. And so anybody who just wants to stare at some of these pictures will get a really good sense of what's going on.
Yeah, and again, I will just say for our listeners, we've got in front of us 2 easels with poster boards. We've got a bunch of different props to go through examples. So while I haven't had this conversation yet, I'm confident that our listeners will certainly get a lot out of it, but they'll probably get the maximal experience by viewing it, whether it's on YouTube or Spotify or elsewhere.
Yeah. You can't, again, I can say picture in your head this and that, and there's an extent to which you can do it, but it just gets hard after a while. So I'm also going to name names in this one very seriously at the end. Maybe some people will be shocked.
What do you mean by naming names? I mean, from private conversations more, I know that you think that there's a lot of miscommunication, and there are probably stronger words than that within the fields of physics and science more generally. But what do you mean by naming
That's what
names?
I mean. I'm gonna name some names that people will be surprised. I am going to tell you they do not understand general relativity.
Okay.
People you would think do understand, ought to understand. Now,
I'm looking forward to that.
well, so I'm not sure if you're looking forward to this. The first name I'm going to name is you.
Okay, great.
From the first episode, I have the quote here, and it's wrong. And so I'm going to start with this thing. So here's what you said. Around 1 hour and 13 minutes in, you said to me, "You are one of the world experts on this subject." No, I'm not.
You're not.
I would not
Okay.
be on anybody's list of a world expert on relativity.
Okay, that's interesting for me to hear, just because, I mean, then why are you giving a presentation on it?
Because I understand it.
Okay.
I mean, this is what you have to. There are real experts, especially on general relativity. There's not that much to say about special relativity. A lot to say about general relativity, and there are real experts. And I'm going to name good names now. If you really want to talk to somebody who can explain things to you, Robert Wald is absolutely at the top of the list. Daniel Sudarsky, top of the list. I mean, I asked Daniel about some of this because he's a guy, you say, what's going on here in general relativity? And he stops and thinks for a few minutes and says, it goes like this. And then you understand it. Those are real experts. And if you want to get, I mean, also, again, I'm going to be naming names. People are going to say, why should we listen to you? You're some philosopher. What the hell? Right?
I hear that a lot. I mean,
that's a reasonable, I have no complaint about people saying that. The first thing is, I'm going to explain this stuff. So I'm not asking you to take my word for anything. So one thing you should do is stop and think about what I'm going to show you. But still, if people are skeptical, you should try to get Robert Wald or Daniel on. I mean, there are other experts, Roger Penrose, George Ellis, but they left general relativity a while ago and they're thinking about other things. They'd be more interested in not talking about that. They've just moved on to other topics, whereas Wald and Sudarsky. If anybody's interested in this, I'm just going to, one other person is Robert Garrosh. This little book, General Relativity from A to B of Garrosh's, I highly recommend for anybody interested in this who's not an expert. He's trying to get at the conceptual foundations of it. So I just wanted to bring that along. So then the question is, why am I talking about this? And the answer is because I understand it. And the people I'm going to be calling out on the other end don't understand it. And that's had very bad and continues to have, I think, very bad consequences for the practice of physics.
Before we get to that point, that I've had some of these people on the podcast.
You are right about that.
Okay.
But I'm going to name also other people you don't have not and will never have, and the names you'll say, what? And then I'm going to show you some quotes, and then you're going to say, wait, that's not right.
Well, it will be interesting in case I have those people on again to hear what they have to say if they see this. Yeah.
Absolutely. I mean, I don't want anybody to take my word for this. The first thing I want them to do is say, oh, I see.
I think that the public probably has a misconception of science where everything is set in stone and everybody agrees upon it, maybe in a similar way to how mathematicians do view math. In a lot of cases, there's agreement once something is proven within a given axiom system. But just like politics, there is a tremendous amount of disagreement within science. And while I really enjoy having people on both sides of issues in politics, I also like doing that for science. And that comes up when we talk about quantum mechanics often. I mean, somebody like you and Sean Carroll have very different views about quantum mechanics in certain aspects. But so it'll be interesting to get different opinions on GR after we have this conversation.
Yeah, let me actually make the contrast with quantum mechanics. I mean, there are a couple points just to set things up for people to understand. One thing to understand is that a physics education, because there's a lot of calculational, it's very calculational, specializes pretty early. And you might think, oh, this person has a PhD in physics, they know all about. And the answer is no, they don't know all about. They don't know all about physics. Maybe they never had a course in condensed matter theory. Maybe they had a kind of a little introduction to relativity and then didn't touch it because they were going on to do quantum theory and particle physics. And that's a whole different set of math they have to learn. A lot of time is spent just learning how to solve equations. You know, learning how to use a Green's function to solve an equation. It's an interesting thing to do. You don't learn much except how to solve the equation. So people specialize. And on top of that, most physics education is not aimed at giving you comprehension. You get the most comprehension when they do classical physics, because there are lots of good people who kind of understand really how classical physics works, and they have demonstrations. And but of course, classical physics is wrong. And when you get to quantum theory, that the first thing David and I said to you many moons ago was, don't talk about interpretations of quantum mechanics, because there's no such theory there, right? There's a formalism. The thing people call interpretations are actually just different theories. They have different postulates about what physically exists. That's not true in relativity. General relativity is a clear, intrinsically clear theory. It's, the more you work with it, the better you understand it. But the number of people who specialize in general relativity isn't that large. And most of the people you talk to are not experts. And even though I'm no expert, I understand it better than they do. I'm just going to say that. And this is what I'm going to be arguing.
I would like to just clarify a bit more about what it means to be an expert versus what it means to merely understand something very well. So you really understand general relativity, but you're not an expert.
Mm-hmm.
Does that mean that you are not advancing the theory in some way? Is that what it means to be an expert? Or you can you can do a lot with the math? Or what does it mean to be an expert?
Yeah, a real expert. I mean, advancing general relativity, it's not anything at this point in itself to be advanced. It's kind of in a way, a completed theory.
Well, I mean, reconciling it with quantum mechanics in some way.
Reconciling it with quantum mechanics, I mean, that's, now you're just trying to rebuild everything somehow. I mean, nobody knows what they're doing there. There's no experts on that. General relativity as general relativity. What I mean is, the real experts, they can actually do the calculations. I mean, they can work stuff out. I couldn't calculate to kill myself. I can explain what's going on.
Okay. And
we're going to just look at some equations at a certain point. I'm going to say this piece means this piece means that. But it's a long distance from there to, exactly how long is it going to take for this probe to get to Jupiter, where you have to actually, calculate something.
Okay.
That's what I mean.
Okay, well, I think this has been a terrific preamble to the discussion, so I'll let you take it from here wherever you want to go.
Good. So let me start with this quote from Einstein. This is from the Schulp volume, Albert Einstein, philosopher, scientist. And anybody, his autobiography there is just a wonderful resource. And he's here talking about, again, the special theory of relativity comes out in 1905. And the general theory, it takes 10 years to get to it. And he knew that's what he needed to do next, was gravity. And so he makes this comment, right? This happened in 1908. And what he is referring to there is the realization you had to go beyond the Lorentz transformations, which we'll talk about a bit. Why were another 7 years required for the construction of the general theory of relativity? The main reason lies in the fact that it's not so easy to free oneself from the idea that coordinates must have an immediate metrical meaning. Okay? So that statement of Einstein explaining what was so hard for him, it's to free yourself of the idea that coordinates automatically mean something. Because when you learn classical physics, you're always using coordinates that in a way do have a metrical meaning. And when you get to general relativity, you're forced to use coordinates that don't have a metrical meaning.
Yeah. And something we discussed is that I should be asking questions during this presentation if I think that there's a term that our audience might not understand.
Yeah.
And one that comes to mind is metrical meaning. We're going to be talking a lot about metric, I'm sure. So
Right.
metrical meaning is a good concept to pin down.
Good. So we're going to talk also about, we're basically talking about geometry here. And geometrical structures, there are different parts of them. The most detailed one is a metric, which means some kind of measure of distance or length. So that includes time. We talked about time metrics. What do clocks measure? Last time in special relativity, we're going to go into that a lot here. They measure the proper time. To do that, there has to be a metrical structure in the space-time that's just there. It's just objective. And somehow the way the clocks are constructed means that the ticking is reflecting these distances, as it were, distances in space-time.
Great.
Yeah.
No, that's very helpful.
So actually there was another quote. Sorry. Another quote I wanted to give, actually a funny one that I sort of, again, to make the distinction between quantum theory, which you do a lot of stuff on, and relativity. This is something actually Raphael Busso said in the one you recently released, and he was poo-pooing the idea of interpreting quantum, talking about interpretations.
I remember well.
And so this is a direct quote. He says, "Why there isn't much of a need for them," that is interpretations, "a very human discomfort with what the theory is trying to tell us. When we want to interpret this discomfort away, we might miss what it's trying to tell us. With quantum mechanics, we seem to have much more difficulty getting to that phase of acceptance and of just letting it tell us how the world works." I think that's exactly the wrong thing to say about quantum theory, because there is no theory.
Mm-hmm.
I mean, you can say, if you adopt a pilot wave approach, then you can say, let the theory tell me what's going on in a two-slit experiment. For example, how are the particles moving, right? Because in that theory, you postulate there are particles that have positions and they have trajectories. And then you can ask the theory in different circumstances what's going to happen. But the idea that there are particles is not generally accepted for quantum, right? Most physicists would say, no, there are no particles. There's nothing orbiting. Mm-hmm. And then they'll say things like, oh, there's stuff popping in and out of existence, whatever. I mean, all of these are different theories. So you can only get to that point where you try and, as it were, listen to the theory by working through a bunch of individual concrete cases when you have a theory. There is no quantum theory in that sense. You can try and ask many worlds people, how exactly do you explain this? Good luck. You can certainly ask pilot wave theory, according to your theory, what's going to happen in this experimental situation, that experiment. Then you can get pretty sharp things, or collapse people. You can say, well, when will these collapses occur and how will they occur for different theories? And they'll give you different answers. So there is a point where, yes, you learn by doing, or you learn by solving, or you learn by looking at individual concrete cases, and you start to get a feel for how things work according to this theory. You can't do that with quantum mechanics, because there is no theory, no agreed upon theory. But you can do it with relativity, because there is one. And that's what we're going to do today.
Yeah, that's a very helpful contrast to draw.
And we're going to start, as I say, for probably the first hour or so, we're not going to try general relativity. We're just going to look at special relativity and some things that happen. Because a lot of the phenomena that people only talk about in the context of discussions of general relativity already occur in special relativity. Much easier to understand there. So we're going to go step by step. Okay?
Yeah.
All right. Now, this thing here.
All right. I'm looking at a circular cutout.
And it's circular for a reason, as you will find out. That's for you.
Okay, awesome.
All right. That is a geometrical object with some geometrical structures on it, right? A blue, a red, and a purple line. And there is just objectively there, and the point is there are no coordinates on that, because we're back to, do the coordinates have metrical meaning in this quote? You got no coordinates there, but you have a geometry. And I can ask you certain questions, like, can you point out the straight line?
Yes, I can do that. There's a straight line, a curvy line for our listeners. There's a straight line, there's a curvy line, then there's a red line with, I don't know how you want to describe that one.
It is made of 4 sections, each of which are straight, but then they're corners, right? It kind of jogs up and jogs back down. Exactly. And so you can make judgments. Which of those are straight? Which of them are curved? Where are there sharp corners? If it's curved, how sharp is the bend? Those are all facts, geometrical facts about those figures. And they're just there. Mm-hmm. Now, if I say, now focus on that blue line, the nice straight one, what's its slope?
Doesn't have one.
Thank you. That's why I had to make it a circle. Mm-hmm. If I had given you those same things on a rectangle, you would have automatically read the edges of the rectangle as a Cartesian coordinate system and probably use, oh, it's at 45 degrees, or it's at, or it's horizontal, or it's vertical, right? Mm-hmm. And that's because you would automatically throw coordinates on it. And I made that a circle so you couldn't, right? Now, the other thing is metric. We talked about metric. Metric has to do with length, with measuring things. So if I wanted to get from one side of that to the other, and I had a choice between going on the blue or the red line, which would be shorter? Blue. Blue shorter, right? For the purple one, it's probably not quite so clear. The blue would be faster, but between, say, the purple and the red, mm-hmm. if you're trying to get from one side to the other, probably can't eyeball it.
Right.
If you wanted to measure the length of the purple one, even if you had a ruler, it'd be a little tricky, right? Because it's curvy.
Yeah.
What you would do is chop it into little tiny sections where each section is closer to being straight, and then use your ruler to measure all the little straight things and then add them up. And then ultimately you do this with calculus, take a limit. Okay, so that's metrical structure. When we talk about lengths of things, we're talking about metrical structure. Good. So the point of having these clear things.
These acetates that you're now.
These acetates are coordinate systems. And I have them as acetates to make it clear that they are different from the actual geometrical thing. So we can just, these are Cartesian coordinates. I've got blue running this way and red running that way. Everybody knows Cartesian coordinates. As soon as I slap these down, now if I said, what's the slope of the blue line? Right? You'd sort of, it's sloping upward in this direction somewhat. And of course, if I'd slapped it down that way, you might say, oh, it's horizontal. If I slapped it down this way, okay? So you see, the idea of a slope is an intrinsically coordinate-dependent concept.
Yeah.
It's not there in the world. Now, this is for people who heard the first one on special relativity. We made the comment, in special relativity, nothing has a speed. There are no speeds because they're like slopes. They're coordinate dependent. If you put down a coordinate system, you can then attribute something a speed. But there's no right or wrong coordinate system. And different ones that are equally valid will just attribute. So right now, we could say we are moving at 99. People sometimes say, what would it be like to move at 99.9999999% the speed of light? Answer, we're doing it right now. It's like this. Because there's some coordinate system, some Lorentz coordinate system in which we are. And it's just as good as the ones which say we're at rest. Okay? So the first thing one has to get a sense of is, what are the coordinate-dependent quantities from the intrinsic objective quantities? All right? We happy? Mm-hmm. Now, we are all used to Cartesian coordinates. Those are the ones we all learn. And we get so used to them, again, we just kind of project them. This is what Einstein was saying. And these coordinates do have a metrical meaning. The distance between this and this line 0 and this one 1, and the distance between here and here and the distance between here and here are all the same. Yeah. Furthermore, the coordinate curves, these guys, the red ones and the blue ones, they're all straight. So it's a rectilinear coordinate system. Furthermore, they always meet at right angles. So it's a rectangular coordinate system. Right. I mean, for anybody just listening, we're just looking at a regular old Cartesian coordinate system, the one you always used in school. We're not doing anything fancy here. And if in your mind, you just picture this square grid.
Right.
And the lines are all straight lines and they meet at right angles. So it's both rectilinear and rectangular. And why do we use coordinates? We use coordinates so that we can translate geometrical statements into algebraic ones having to do with numbers. In order to translate geometry into algebra and solve it algebraically, we need this translation scheme to take a geometrical problem and convert it into a numerical one, and then convert it back. And the coordinate system allows us to do that. This is what, if you read Descartes' book La Géométrie, where he's doing this, he didn't actually introduce these, what we call Cartesian coordinates, but he's very aware. He says, look, there are these powerful methods for solving numerical problems. I wish I could use them in geometry. Because, you know, what did people use in geometry? They used Euclid. They used straight edge and compass. No numbers. And so you couldn't, in any obvious way, use algebraic method to solve geometrical problems. And the great step forward for calculation was to introduce coordinates, translate your geometrical problem into an algebraic one, solve it algebraically, and then translate back. Sometimes it doesn't quite work out. You end up with imaginary numbers and complex numbers, and people puzzled about what there's an interesting story there. We're not going to go into that. But you sort of have to use coordinates, but you always have to bear in mind that the coordinates are not intrinsic if you're doing relativity or if you're doing physics in general. The numbers are not intrinsic. They're things that we stick on by settling on a coordinate system. Yeah. So that's Cartesian coordinates, and you'll notice we can rotate, right? We can, as you know, with Cartesian coordinates, I can choose any point here as the origin, 0, 0. I can then twist this so the x-axis and the y-axis run whichever way I want. They always run at right angles. So there are an infinite number of different Cartesian coordinate systems I can throw down on this. The other coordinate system that probably everybody is familiar with, but it's going to be very useful soon, is this one, which is polar coordinates.
And I do not think, I don't know if everybody's familiar with polar coordinates.
Okay, if you're not familiar with polar coordinates, as there's an origin in the Cartesian one, there's a very special origin in the polar one. Any arbitrary point. I mean, it's not that there's anything special about that point. I can stick it anywhere I want. That's the origin of my system.
Right. And how would you describe how this acetate looks?
Okay, this thing looks like a dartboard.
Right.
That is, then the coordinate curves, in the blue ones are concentric circles that get larger and larger. So this is at a fixed radius. Take all the points at some distance, then go out, take all the points at twice the distance, take all the points at 3 times the distance, and so on. I mean, that gives you this, the r coordinate, what's called the r coordinate, the radius. And then these red lines that are going straight out from the origin, those give you the angle. So the angle changes, and the angle is theta. So you, instead of using x and y, which you do in Cartesian coordinates, you use r and theta. And every, almost, we're going to come to that in a second, almost every point gets, again, a kind of unique coordinate address. So you say, oh, go out 5 units or 3 units for the radius and at an angle of 45 degrees. And you can do that, right? Because you go here and you go out this one. And, oh, you're talking about this point, right? R theta. Nothing's changed in the geometry. All the lines are still lines. All the straight lines are still straight lines. All the distances are what they are. Okay? I'm just describing them using a different coordinate system. And the coordinates still here have a kind of metrical meaning, if we take Einstein's quote, although it's different because obviously the r and theta are working a bit differently than the x and y in Cartesian coordinates.
But there are fixed distances between all points.
Mm-hmm. They're going to be, well, we'll talk about distance. Yeah, we'll bear that question in mind.
Okay.
We said and we're doing this all for the Euclidean plane, right? I mean, what I've got, this disk is a Euclidean plane. We're putting coordinates on it. The thing is, there's a peculiarity about these coordinates. There's nothing peculiar about the space. Space is just there. There's something peculiar about the coordinates. They have some problems. In the Cartesian case, every point gets a unique address, x, y, right? An x value and a y value. And here, many do, like we can go out 3 units at 45 degrees, that takes us there. But there are some funny things that happen with these coordinates. One thing that happens is right at the center, r is 0, because you're 0 distance from the center. So, but what's the angle? What's theta? It doesn't have one. All of these straight red lines are all points at the same angle, and they all meet at the origin. So it just doesn't have a theta. Now, nothing funny happened in the space there. It's just something funny happened to the coordinates there. So that's called a coordinate singularity. And the word singularity is going to come up a lot when we get to general relativity. And you have to be clear between a physical singularity, which is something going on in the space, and a mere coordinate singularity, which is a breakdown of the coordinate system. Okay? The other funny things that happens here is if I go out to 1 unit, so I'm at r equals 1, and I start at theta equals 0, which would be here. And now I start just going around this circle. So theta is 0, and now it's going up. I'm measuring in radians. So when I get halfway around, it's at pi. It goes up to 3/2 pi. It goes up. It almost gets to 2 pi, and then I'm back to where I started. And then all of a sudden, it jumps back to 0. That's a discontinuous jump. So the coordinates aren't everywhere continuous. Now, if I don't like that, I can say, well, why don't I just keep going up to 2 pi? Well, that's okay, except now this one and the same point has 2 different coordinate addresses. It's both 1, 0 and 1, 2 pi and 1, 4 pi and 1, because I can keep going around and around and around and around. So sometimes you do that, but you got to do something funny. Not because anything funny is happening in the space, but again, something funny is happening with the coordinates. And early on, after general relativity was developed, certain solutions to the equations were found that had coordinate singularities. The coordinate systems broke down, and people didn't realize it. And they thought something funny was happening in space-time. And this took a long time for people to get clear about. And that's part of what Einstein's reflecting here, is you can get confused about coordinates. Now, if we think about these coordinates, oh, I know what I was going to say. So I said in the case of the Cartesian coordinates, all the coordinate curves that are straight, so it's rectilinear. Here, the red ones going out, the ones that give you points at the same angle, those are straight. But the circles obviously are not straight.
Right.
So this is not rectilinear. But every red meets every blue at a right angle, because of course the radius meets the circle at a right angle. So it is rectangular. It's not rectilinear. Okay? So those are just two different coordinate systems that we can put down on our little space. And so what this, and this has more math-looking stuff than any other of our things.
So you're pointing to this, the second poster that's up right now.
And basically what this is just talking about in the two-dimensional Euclidean plane, which is what we have there are distances between points. And you can calculate those distances using coordinates. But of course, depending on the coordinate system, the calculation goes a little differently. So in Cartesian coordinates, we have this very simple formula that the distance between point A and point B, if I want to know how far any pair of points A and B are, A has an X and a Y coordinate, B has an X and a Y coordinate. And this is something everybody learned.
In Algebra 1, probably.
Exactly. You just take the difference in the X coordinates and square it, take the difference in the Y coordinates and square it, add those up and take the square root. That's the Pythagorean theorem. That gives you the distance between A and B, right? And so if we, instead of writing XA minus XB, we write this big delta X, that's a kind of big difference between the X coordinates, take that and square it, take the difference between the Y coordinates and square it, add them up and take the square root. That gives me the distance between A and B for any 2 points, wherever they are. That's a nice, simple way to get that. So this is the formula for the complete, for any 2 points. Just give me the coordinates of this one, the coordinates of that one, plug them into this one formula, bang, that gives me the distance. Now, it turns out to be very convenient. Instead of taking the distances between any pair of points, to only take distances between very, very nearby points, very close points. So where this big delta can be a big difference in the x's and a big difference in the y's, the little dx and dy mean I'm looking at points that are really close to each other. So their differences in coordinates are very small, and I make them as small as I like. And then this same formula, which here gives me the distance, now gives me the infinitesimal distance between these 2 points, ds. So the little d here means I'm doing something infinitesimal. And then to get the distance between 2 points, I just draw a straight line between them and measure its length using that. And so that's how I get far distances, right? I only have little close distances, and then I add them up. Just as we talked about calculating the length of that purple curve, you just take little, chop it into little pieces and measure them and then add up all the little pieces. And that's basically what differential calculus is doing for you. Now, in my polar coordinates, I can do the same thing.
And the polar coordinates, again, are the dartboard coordinates.
Are the dartboard coordinates. I've got r, for my 2 points A and B, each has an r value and each has a theta value. So I've got RA and RB, theta A and theta B. This is just the big D formula, the distance between any 2 points in polar coordinates. You'll notice it sort of looks like the Cartesian one. You've got the square root, you've got the square root of RA squared plus RB squared. Then you have this other term, minus 2RA RB cosine theta A theta B, okay? That's just what goes in there. So it's a kind of more complicated formula. You can do it. When we go and look at just tiny little differences in the dartboard coordinates, when I zoom in, because they're rectangular, they look more and more like Cartesian coordinates. So if I go down to the infinitesimal form, the little ds form, now it looks very much like the Cartesian one. Here it's the square root of dx squared plus dy squared, and here it's the square root of dr squared, the difference in their radius, plus r squared d theta squared. So it's the difference in their angle, but that difference in their angle is multiplied by r, which makes sense, because the further you are from the center, the more a little change in your angle gives you a bigger change in your distance, right? If you swing a little bit, the further out you go, that little angular swing becomes a bigger and bigger distance.
Because these aren't parallel lines.
Exactly, because these are not parallel lines, and they're diverging. Mm-hmm. So, and the fact that the polar coordinates are rectangular again, you lose this other third term. You just have these two terms here, and this funny third term with the cosine disappears in the limit as you go down to here. So you can sort of see there's a connection here. Now, I'm going to give you another coordinate system. I guarantee you've never seen this one. I guarantee you've never seen this one. Where is it? Ah, here it is. Try those coordinates.
Yes, I have not seen the ocean wavy line coordinate system.
That coordinate system doesn't have a name because I just made it up. It's a whole bunch of wavy blue lines that are different. I mean, they have different curvatures and so on, but they never intersect. And a bunch of wavy red lines that are wavy and they never intersect. And so every point lies at the intersection of a unique blue and a unique red. So I can use those as coordinates. If I give numbers to all the blue lines and numbers to all the red lines, I can then identify every point by its coordinate address. But in this case, it's a perfectly good coordinate sense. But now Einstein's comment is very clear. Here, the coordinates have no immediate metrical meaning, right? I mean, if you say, well, the red difference between them, one is that red equals 1 and the other is red equals 2. Well, in some places they're very close. In some places they're very far. Right. So there's no significance of the coordinates per se. That's what Einstein had a hard time wrapping his head around. And when you get to general relativity, you're forced into this. There are no nice coordinate systems in general at all that have these beautiful little formulas. So there's a very general formula, and this is the last thing I'm going to do here, just so people see it, which is for arbitrary coordinates, right? So any old coordinate system, even this funny red-blue one you've got, there is a way to express this tiny little infinitesimal distance between 2 points as some function we can just call f1. My two coordinates are now alpha and beta. Some function f1 of alpha beta times d alpha squared, some other function f2 of alpha beta times d beta squared, some other function f3 of alpha beta times d alpha d beta. And this is called a quadratic form because you have alpha squared, beta squared, and alpha beta. Those are all kind of second power, right? You're multiplying two together and you take the square root. This is in a completely general formula, but as you change the coordinate system, these functions change. So you can see the Cartesian functions count as an instance of this, where f1 equals 1, f2 equals 1, and f3 equals 0. And the polar ones count, where f1 equals 1, f2 equals r squared, and f3 equals 0. And so when you get to general relativity, or even if you're just doing Euclidean geometry, there is this general way of expressing the geometry in terms of any coordinate system. And yet you have to do that because in the end, there are no nice coordinate systems. And if you get confused the way Einstein was, it's really hard. So one of the main things I want to do is separate the coordinate dependent quantities from the ones that are just there, that are in the space itself. Those are the ones we care about. And the coordinates are just a means to them. Okay? So that's the whole beginning here. And what I want to now do is if everybody understands that, just for Euclidean geometry that everybody's familiar with, now we can do special relativity. And I mentioned this in the last interview, that this formula here for the distance, which is the square root of dx squared plus dy squared, if you just turn that plus into a minus, and you call, instead of x, you call that t, now we're doing special relativity. That gives us the fundamental distance, which is this invariant interval between any 2 points. So you can, I mentioned before, you can just plug in. There are going to be analogs in special relativity to Cartesian coordinates. Those are called Lorentz coordinates. And there are also going to be analogs to polar coordinates. They're called Rindler coordinates. And I'm going to show you those. And you're going to see they're kind of similar, and they're in certain ways kind of different. But it's very systematic. And once you get used to it, you can see what's going on in a very clear way. All right, so that's why, so all of this down to here was about Euclidean space. We're now going to Minkowski four-dimensional space-time. So now we're going to pick up from the last talk. We've got a four-dimensional space-time. We said it has a light cone structure. And that the fundamental quantity that Cox measures is the proper time. And the proper time is this I unit. This is called the invariant, relativistic invariant interval. And we can do everything the same way. We say, well, Minkowski space-time is flat. It's not curved, just like Euclidean space is flat. It's not curved. We'll go in later what curvature means, but we don't need to do that yet because we're still doing special relativity. And that flatness means it's got nice symmetries. It looks the same everywhere. And because of those symmetries, they're a nice coordinate system.
So for those of our viewers and listeners who haven't watched the last episode, though, can you do a quick gloss just on what special relativity is so people can follow along going forward?
So special relativity was what we now call the theory that Einstein came up with in 1905, which was a way to formulate really electromagnetic theory. Maxwellian electromagnetic theory. Maxwell came up with his theory thinking in terms of space and time as Newton had understood them. And Einstein found some of the features of Maxwellian electromagnetic theory very puzzling. We talked about this in the episode. What he found especially puzzling was that there were physical effects that only seemed to depend on the relative, the effect only depended on the relative speed of two objects. So we talked about an experiment where you have a coil of wire attached to an ammeter that measures current and a magnet that goes through it, and that induces an electrical current. And you can measure how much current there is. And it turns out how much current there is only depends on the relative speeds, how fast the magnet is moving with respect to the coil or the coil is moving with respect to the magnet. But in the theory as Maxwell wrote it down, the explanation of that current is quite different when the coil is at rest and the magnet is moving, as opposed to when the magnet is at rest and the coil is moving. And Einstein didn't think that sounded right. He thought, well, if really the current only depends on the relative speed, the physical explanation shouldn't go quite differently depending upon whether this is moving and that's at rest, or that's moving at this, or they're both moving, or whatever. And so in the special theory of relativity, you replace Newton's picture of space and time, which I'll have some pictures of here, with special relativity, which is Minkowski space-time. And it has some surprising features, but they're easy to picture. And actually, we can get to the contrast. I think that's actually what's going to come up. Oh, all right. So let's do one other thing before we get to the pictures. So here are some comments that Einstein made about the way he thought of physics and the direction physics had been going in.
Great. No, I really enjoyed getting into Einstein's head a bit in the last episode, which I recently just learned that his last name is Onestone.
Mm-hmm.
And this is another interesting story that I learned from a German friend of mine. But I guess when a lot of Jews immigrated to Germany from Russia and elsewhere, the officials would just give them names that they thought were humorous and ridiculous to mock them.
Oh.
And that's why a lot of these names are kind of nonsensical, like Einstein or I just thought that was interesting.
I hadn't heard that. Well, one always hears coming to the United States that sometimes at Ellis Island people would be given or adopt new names because they think their old ones wouldn't fit in so well. And by the way, this quote, I mean, we're not going to get into quantum theory here, but if you want to see the conflict between relativity and quantum theory, it's in this quote.
Okay.
So this is in a letter that Einstein wrote to Bohr, and I'll just read it. So he says, if one asks what, irrespective of quantum mechanics, right? Einstein is very careful to say, I'm not talking about quantum mechanics, because he never was happy with that, is characteristic of the world of ideas of physics, one is first of all struck by the following. The concepts of physics relate to a real outside world. That is, ideas are established relating to things such as bodies, fields, etc., which claim real existence that is independent of the perceiving subject. Ideas which, on the other hand, have been brought into as secure a relationship as possible with the sense data. So there's a real world out there, right? And the ideas of physics are describing it as they are, not about how they seem to us, but nonetheless, we try to connect them up with our perceptions as strongly as we can. It is further characteristic of these physical objects that they are thought of as arranged in a space-time continuum. So we've got this space-time that these things live in. An essential aspect of this arrangement of things in physics is that they lay claim at a certain time to an existence independent of one another, provided these objects are situated in different parts of space. So, okay, I have this piece of paper and this hand, they're in different parts of space. There should be some complete physical description of this that doesn't mention that, some complete physical description of this that doesn't mention that, right? Unless one makes this kind of assumption about the independence of the existence, the being thus of objects which are far apart from one another in space, which stems in the first place from everyday thinking, physical thinking in the familiar sense would not be possible. Now, it's this final comment that's going to be of some interest to us. So he says, this principle of locality, that you can kind of isolate spatially separated things and talk about them independently of each other. He says, this principle has been carried to extremes in the field theory by localizing the elementary objects on which it is based, which are the fields, and which exist independently of each other, as well as the elementary laws which have been postulated for it in the infinitely small four-dimensional elements of space. So what he's saying is, in field theory, in classical field theory, like Maxwellian electromagnetics, you have these fields, electric fields, magnetic fields, they're defined everywhere. But you can take any little region of space and say, okay, what's the electric and magnetic field there? What's the electric magnetic field there? You can describe the one here independently of that one. You can describe the one here. And the fundamental laws that Maxwell postulates can be stated just in terms of what's going on in these tiny little regions. So you can check, if you want to know, are Maxwell's laws being satisfied here? It's sufficient to check region, little piece by little piece. Are they satisfied here? Are they satisfied here? And that's because the laws themselves have, as it were, been shrunk down to these little regions. That was what Einstein thought the progress of physics since Newton had been. And that's when he says, irrespective of quantum mechanics, because quantum mechanics, because of entanglement and the holism, explodes out the other direction, right? It sort of says, no, you can't describe this particle without mentioning that one way over there, right? And that gives you the spooky action at a distance, all the stuff Einstein didn't like. Here's another quote about this, which is going to be relevant to a lot of stuff we're going to be talking about. This is in the autobiographical notes I mentioned. And he gives an account of relativity there. And he does it the way everybody does it. He says, okay, I've got clocks and measuring rods, right? And I'm going to talk about how they behave, right? And I'm going to somehow describe the space-time structure in terms of these instruments. So let's just see what he says. He says, first, a remark concerning the theory as characterized above. So he's given an account of it. One is struck by the fact that the theory, except for the four-dimensional space, introduces two kinds of physical things. That is, one, on the one hand, measuring rods and clocks, and two, all other things, the electromagnetic field, the material point, and so on. This is in a certain sense inconsistent. And this is Einstein, again, tracking exactly what he's just done and noticing it doesn't really make sense. Or there's a promissory note has been written that he hasn't cashed. And he's aware of that, and he's talking about that here. This, in a certain sense, is inconsistent. Strictly speaking, measuring rods and clocks would have to be represented as solutions of the basic equations, objects consisting of moving atomic configurations, not, as it were, as theoretically self-sufficient entities, right? You can't say, oh yeah, they're the electric fields, the magnetic fields, the particles, and by the way, also the clocks and the rods, right? I mean, clocks and rods, whatever they are at the end of the day, are made up of electromagnetic fields and particles interacting in some way in some structure, right? Nonetheless, whenever you present this, you treat those instruments as special somehow, and you don't really give an account of how they work. But you have to. At the end of the day, if you're going to have a really complete physical theory, you have to. However, now, why didn't he do that? Why didn't he just say, well, here's how the clocks work, here's how the rods work? Because they didn't know. Because they didn't have a theory. Right? They didn't even really understand the stability of matter, right? They didn't have quark theory, they didn't have, all right? So, however, the procedure justifies itself because it was clear from the very beginning that the postulates of the theory are not strong enough, that in this case, Maxwellian electrodynamics, are not strong enough to deduce from them sufficiently complete equations for the physical events sufficiently free from arbitrariness in order to base upon such a foundation a theory of measuring rods and clocks. So he said, we just couldn't do it. Not in a position to do it. If one did not wish to forego a physical interpretation of the coordinates in general, something which in itself would be possible, it was better to permit such inconsistency, right? To say, look, at this stage of construction, we're going to treat the clocks and rods as somehow different from the electromagnetic fields and the particles. We're going to treat the clocks and rods, give an account of space-time in terms of them, then write down these laws of electromagnetic theory in terms of those, and talk about the fields. He says, with the obligation, however, of eliminating it at a later stage of the theory. But one must not legalize the mentioned sin so far as to imagine that the intervals are physical entities of a special type, intrinsically different from other physical variables. And he makes this comment. So, I mean, there's a lot to take in here, and I don't want to spend a lot of time on it, but one thing you notice is Einstein, again, very sensitive to what he's doing. He's just given you an overview, a kind of sort of standardish overview of special relativity, saying, well, clocks and rods do this. He says, well, yeah, that's not really quite, I can't really say that legitimately, right? At the end of the day, I've got to give you a physical account of the clocks and rods. You could call this the special relativistic measurement problem, if you like. But there was no reason to think, as with the measurement problem in certain versions of quantum theory, you see, it's going to go badly. Einstein thought, no, there's no reason to think it'll go badly, but I still can't do it yet, right? So we're going to talk a lot about that, but we're going to basically adopt, for the most part, the view that Einstein does here. We're going to say, look, we've got some instruments. We've got clocks. They measure this interval. We talked about that last time in Minkowski's spacetime. The time-like interval along a path gives you the length of the path. And we're going to say clocks measure that. If you say, how does a clock do that? I'm going to say, I'm not going to tell you. I mean, I could I could make up pretend clocks. Everybody does this. They say, well, if it was a light clock where there's a light ray bouncing around between two mirrors, okay, nobody makes light clocks. There are no such things. These are just fantasies, okay?
Right.
If you want to know how this thing works, that's really complicated. Yeah, the Apple Watch, right? Or a quartz crystal watch, or a mechanical watch with a spring in it. Okay, very complicated story. Now, it turns out they're very simple systems that kind of function like clocks because they're unstable particles that decay, like muons. And because there's a characteristic average time of decay called the half-life. And a muon doesn't seem to have any internal structure at all. It's like an electron. A muon's like a heavy electron. As far as we know, it has no internal mechanism structure at all. But still, it has this decay time, this characteristic decay time. And so you can kind of use muon decays as a kind of clock, the way we use radioactive carbon as a clock when we dig up a dinosaur bone and we're trying to figure out when was that dinosaur alive. We can check how much of the carbon-14 in it has decayed, and that gives us an idea how long it's been, because the decays happen on average at a certain rate. So there are, now I should mention, because this is going to be very important for what we're about to do, I'm not going to talk much about rods. Rods are really complicated. Clocks are fine, and light rays are fine. And at the end of the day, we're going to talk about gyroscopes. So the three instruments we're going to talk about today that as directly as possible tie into the space-time structure are clocks, light rays, and gyroscopes.
And
not
I think
rods.
You've got some gyroscopes.
I've got some gyroscopes.
No light clocks, just gyroscopes.
Yeah, no, the clocks, I'm going to assume, do measure this proper time. We're not really going to try and dissect them. We're going to start thinking about doing physics directly in terms of geometry. The first thing conceptually is to say, can I state the laws of physics directly in terms of space-time geometry, in terms of concepts of space-time geometry? Newton was very careful, we went over last time in his Scholium on Space and Time, to explain the structure of space and time as he was postulating it to be. But he didn't then state his laws as cleanly just in terms of the space-time structure as he might have. So I'm going to do that translation for his first two laws. So here's what Newton says, Law 1. Every body perseveres in its state either of rest or of uniform motion in a straight line, except insofar as it is compelled to change its state by impressed forces. Right? So that's my translation of Newton's Latin. You'll notice it's kind of a funny law because it's got this or in it, right? It's a kind of disjunctive law. It says if a body is at rest and no forces are impressed on it, it'll stay at rest. And if it's moving and no forces are impressed on it, it'll continue moving in a straight line at a constant rate. Uniform, straight motion. And for Newton, those are kind of different, slightly different things. You've got absolute rest and then you've got absolute motion. And absolute motion can be uniform in its rate and always in the same direction. And he's saying if you don't put any forces on something, that's what it will naturally do. This picture is supposed to show space and time as Newton conceived of them.
Can you describe them for our listeners?
And so you've got these flat planes, horizontal planes, that represent different moments of time. So, at time t equals 0, this is everything going on in the universe. At time t equals 1, at time t equals 2. As time goes on, you have absolute time that's ticking away. You can say it's ticking away uniformly, but that's trivial because there's no other time relative to which it could be non-uniform, right? It's ticking away at 1 second per second because it has to. People get very confused. They say, how can time pass at 1 second per second? You say, no, the question is, how could it not pass at 1 second per second? It is the standard, right, by which time distances, metric, are defined. So we have time ticking along. What we've done in this diagram is each of these planes, planes of instantaneity or instants of time, are represented by two-dimensional Euclidean planes. Of course, for Newton, that would be really three-dimensional Euclidean space, but we can't represent 4 dimensions on a diagram, so we get rid of one. And now, the idea that Newton has here, if we now translate this into the language of space-time, the first law says this: the trajectory of a body is represented by a straight line in space in a space-time diagram, except insofar as it's compelled to change its state by impressed forces. So you'd say, look, here, this purple line is a particle moving through space-time, no forces on it, right? And you can see in the diagram it's moving along a straight trajectory through space-time. And the blue one is straight, and the red one is straight. No forces, no forces.
So for our audio listeners again, there's a ladder-looking structure moving through the planes on the left, and then a helix moving through the structure on the right.
So what this represents, if you go back and listen to the first talk, Newton talks about a case where you've got 2 spheres, and this is connected with his bucket, but it's the same idea. 2 spheres tied together by a cord. And he says it could be that that system is rotating around its center of mass, or it might not be, right? If it's not, then there's no tension in the cord. The cord will be completely slack. It won't be putting any force on anything. On this side of the diagram, the ladder-like thing is what a non-rotating such system would look like in space-time. And you'll notice all the lines are straight, so there are no forces. There don't have to be any forces. If the entire system is rotating, I've got the blue sphere and the red sphere, but the whole thing is rotating, then you'll notice it looks now like a strand of DNA. It looks like a double helix. It's very twisty. Mm-hmm. And what the first law says is, oh, there are some forces here. There have to be some forces here to get this twist going on.
This diagram's quite neat.
And those forces are, of course, provided by the cord connecting them, and there would be tension in the cord. And as I said last time, the faster they're spinning, the more twisty that is, the greater the tension has to be, right? So we can think of Newton's first law as, in space-time, what happens to a particle if there are no forces? Answer, like this purple one, straight line, or this one, straight line, straight line. Then, well, what if there are forces? That's what the second law is about. Newton's second law, the way he put it, the change in motion, if you impress a force on something, is proportional to the impressed motive force and is made along the straight line on which the force is impressed. So if you put a force on an object, it'll cause a deviation from what it would have done in the direction of the force, and a stronger deviation, the stronger the force. And that gives us these bends, right? These twists in space-time. So if we just translate the second law into space-time language, geometrical language, the trajectory of a body subjected to an impressed force is bent, and the bending is in the direction and proportional to the force impressed, okay? So acceleration, which is a central concept for Newton, is expressed geometrically as curvature, the bending of these trajectories of particles in space-time. That's what acceleration is. Now, the other thing to notice, and now we're going to get going to do some kind of tricky stuff, is I said in the first point, think of this blue and this red as these spheres. They're tied together by a cord. The cord is represented by the black line, and it's keeping them together. But now I want you to imagine that something else is going on. That is, you've got clocks. You've got a clock on the blue and a clock on the red. And these lines indicate when these clocks, you can even have clocks strung out along the cord, ticking of the clocks. So the clocks, if they're the same make and they're tied into absolute time, are ticking at this constant rate. So you see the little steps of the ladder, the rungs of the ladder are equally spaced, and they're equally spaced to these connecting things in the double helix, in the twisty one. In addition, I mean, one thing I wanted to illustrate in this diagram was the difference between a rotating system and a non-rotating system. And one thing we talked about last time is that that difference, what Newton argues with the bucket, is that that is not about relative motion of anything. Because in none of these cases is anything moving, in neither in the ladder, where you've got the red and the blue, they're just a constant distance apart. They're not getting nearer or closer to each other. There's no relative motion. Nor in the twisty, in the double helix one, they're also not getting closer, nearer or closer, right? They're not approaching or receding. So there's no relative motion. These are all systems where the material parts are at relative rest. But there's a difference, and that was Newton's argument, difference between the rotating and the non-rotating systems, which you see in these space-time diagrams show up as these curvatures that correspond to accelerations. Okay? Now, as I say, if we now add to this the idea of putting clocks, for Newton, a good clock is tied into absolute time. You have these planes of absolute simultaneity, and a good clocks will be ticking so that at equal intervals of time they tick. And that's going to be true whether they're spinning or not spinning or whatever. They're just going to tick along to absolute time. So you see the number of connecting links along the ladder between two planes is the same as the number of connecting links on the twisted one between two planes, because the clocks for Newton would be completely unaffected by motion if they're good clocks. Okay? The nice thing about doing this is that this is Newton. We've got Newtonian spacetime here. It's got absolute time, absolute simultaneity. It's got the additional structure you need to define these straight lines, to define curves and how curved they are. When we go to special relativity, we get rid of that, right? We throw that away. Well, before we go there, let's talk about these levels of structure. We're now gonna change out, and we're not going to see Newtonian spacetime again for the rest of this entire talk. So this is where Newton was, and this is where Maxwell was. And now we're going to talk about a new spacetime structure, the spacetime structure of special relativity or Minkowski spacetime. Here, we are now trying to think directly in terms of spacetime geometry, which means just thinking directly in terms of geometry. So what kind of geometrical structures are there in a geometrical space? And in particular, what kind of geometrical structures are there intrinsic to Minkowski spacetime? So we want to understand what kind of geometrical structure is there in Minkowski spacetime. We saw that in Newtonian spacetime, you've got absolute time, you've got these planes of absolute simultaneity. In the first one we mentioned, this is called a foliation, because you're taking the whole spacetime and chopping it into these individual leaves in a unique way.
Mm-hmm.
We get rid of that to go to Minkowski spacetime, to go to the spacetime of special relativity. We don't have absolute simultaneity anymore. We don't have a foliation. Now we have to talk about what we do have. So the first thing we have is what's called a conformal or a light cone structure. And so that's what it looks like. That is, whereas on this side, for Newton, we've got these flat planes of absolute simultaneity. In Minkowski spacetime, at every point, there is a light cone. At every point, the light cone is divided. The blue part here is the future light cone. The red part is the past light cone.
So it looks like an hourglass.
It looks like an hourglass. It's a normal double cone, and the cone point is the unique point that each of these light cones is associated with. So every event in space-time gets its own light cone.
And what is a light cone?
It is, I mean, the first thing to understand is that this is just part of the intrinsic structure, just as these planes of simultaneity are part of the intrinsic structure. Now, it's called a light cone because in a vacuum, that's where light will go. Light will travel along the light cone. In a vacuum, if light is described by Maxwell's equations. So we said Einstein got to special relativity by thinking about Maxwellian electrodynamics. In Maxwellian electrodynamics, there are electromagnetic waves. And the postulate is that that's what light is. Light is an electromagnetic wave. How do these waves, as it were, propagate? How do they go through space-time? How do they know where to go? And this was, we talked about in the first one, the original thought was, while they're waves, there must be a medium, there must be some luminiferous ether or some other kind of weird medium that these are vibrations in or stresses in or strains in. They couldn't work that out. They couldn't make any sense of it. And at the end of the day, you just say, no, there's just an intrinsic structure to space-time itself, which, in terms of which Maxwell's equations are written. And once you write them in terms of it, you see that these waves will propagate along these light cones. Now, if you want to know where they came from, we had before that invariant interval I. If we set I to 0, you might think, wait, if there are two points and there's 0 distance between them, then they're the same point. That's true in Euclid. It's not true here. So this is the fact that I can go to 0 for distinct events means this is one of the big changes from Euclid to Minkowski, from what we call a Riemannian to a pseudo-Riemannian metrical structure. So you just have to get used to that. In a way, if I just pick this point on this diagram, we've got all of these light cones here. If I pick one cone point, I've got the future light cone. All of those are at interval 0 from here. And along the past light cone, all of those are of 0 interval from that cone point. It's all zeros. Now, I will make a comment here I don't want to go into a lot. We said that clocks measure the interval along their trajectory. People often say, oh, then for light, time doesn't pass because the interval is 0. That's not right. That's just incorrect. It's a complicated story. Basically, the reason you have to put in 0 there is that 0 doesn't bear any ratios to any numbers. But it's not that people, oh, you know, for a photon, time doesn't pass. That's not right. You create a photon, you send it sequentially through 4 different filters. It'll go through those filters in a time order, right? It'll be created here, then it'll hit this filter, then later it'll hit that filter. There'll even be ratios of times between going through these filters if it's going straight. So this idea that time doesn't pass for photons, that's not right. Okay, but that's a little more technical than I want to get into.
That's very helpful, though.
Yeah, it's one of the things that people get very confused
Right, it's a
about.
big myth.
Yeah, that is a big myth. Anyway, so what kind of intrinsic structure does this have? Well, the first one here we call the conformal structure, the light cone structure, and we represent it on this diagram by putting a light cone in at every point. And if you imagine a little ray of light being emitted from this one and going that way, I really don't have to do the whole light cone, because once it gets to here, I could just draw the light cone at the new point, and as long as it keeps going the same direction, right? And again, if there's no forces on it, it'll keep going the same direction. I can just build up these light cones little bit by little bit. There's something else here, which is you have what's called an inertial or an affine structure, which means there's a distinction here between straight and curved lines. Some of them are straight and some of them are curved, just as on the one we started with in Euclid. That has an affine structure. The purple line is curved. The blue line is straight. The red line is straight except at these points where it bends, right? That kind of structure also exists in Minkowski spacetime, okay? That's why in Minkowski spacetime you can write Newton's first law without change from the way Newton did. You say if there are no forces on a particle, it travels along a straight line in spacetime. And if there is a force on it, it'll cause that line to bend. Now, you have to worry about quantifying the bend and so on, but that's the basic picture. Acceleration is bending. Then there's this metrical structure, which I've said here it's a pseudo-metrical structure because it has this, works in a funny way with respect to the triangle inequality. But as long as you've got these lines, like our blue and red spheres, both the spinning ones and the non-spinning ones, these lines have lengths that are given by the proper time. That's a metrical structure, okay? And that's what clocks read. That's the fundamental hypothesis. And then there's also a notion, we'll get to this much later, but I'll mention it here, of parallel transport, and this gets connected to the physical behavior of gyroscopes. So again, we've got light, we've got clocks, we've got gyroscopes. We don't have rods. Why not? I mean, Einstein talks about rods. Everybody talks about clocks and rods, clocks and rods, clocks and rods. Well, one thing you might notice is nobody ever has, and nobody ever will, measure the distance from the Earth to the moon by rods, by taking meter sticks and sticking them, right? That's not how we do it. We can't do it that way. How do we measure? We can measure the distance to the moon, as it were, quite precisely by bouncing light, by radar ranging. We bounce light off it in time. How long did it take the light to get to the moon, bounce off the mirror, and come back? What do I need for that? I need light, I need a mirror, I need a clock.
Yeah.
Right?
Yeah.
So the actual instruments we use aren't rods. And furthermore, rods are really complicated, and we're going to get into that. So now we can take, this is where we were, and now I can put it up. I'll leave that. We'll come back to that later. We can now take our rotating and non-rotating system of spheres tied together, the Minkowski one, the special relativistic one on this side. They look pretty similar, right? Except we've got a ladder here, we've got a double helix, just as we had a ladder here and a double helix. We got rid of these planes of absolute simultaneity, because that's part of Newton's structure, that's not part of the Einstein structure. We've put in the light cones, that's part of Einstein's structure, that's not part of Newton's structure. We still have the distinction between the non-rotating system, where these are straight, and this purple particle, that's still straight, no forces on it, and the rotating system. So this is Newton's bucket again. There's an absolute distinction between rotating and non-rotating systems. Has nothing to do with galaxies out there or anything else, it's just in the space-time structure. But you might notice there's another difference here. If these are now the ticking of the clocks, and you'll understand this from the last one, but I'll go through the audience so they understand. There are fewer of these ticks in the rotating system than in the non-rotating system.
So fewer rungs on the helix.
Fewer
ladder.
rungs on the helix than there are rungs on the ladder. Why is that? Well, if you remember, what happens when we go to Minkowski spacetime is we get this funny kind of inversion that these curved trajectories of the rotating system, in Euclidean space, these would be longer. But in Minkowski spacetime, they're shorter. The longest lengths are the straight ones, right? That's a fundamental, if you've got an absolutely straight trajectory, that is at least locally the longest one. If you deviate it from it in any way, it'll get shorter. So in the rotating system, we have a difference that doesn't show up in Newton. The clocks will show less time elapsed if they're rotating than if they're not rotating. So it's yet another immediate, physical, observable effect of the space-time geometry and of the difference between rotating and non-rotating systems. That doesn't involve sloshing, it doesn't involve forces, it just involves ticking. And so you'll see here, it's going between the top and the bottom, 1, 2, well, let's see, if we start here at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 ticks, and here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the longer the rotating clocks rotate and the non-rotating clocks don't rotate, the greater the difference between how much time they show. So we talked last time about time travel into the future. Normally people talk about getting into a rocket going far away. You don't really have to go into a rocket and go really fast around, right? Orbit the Earth in something like, you wouldn't really be orbiting, but just go around the Earth in a very tight spiral. And your clocks on your thing, when you go back to Earth, much less time will have passed than the people on Earth.
Good way to time travel.
Yeah.
Could you also just get into something that spins very quickly?
Yes.
Okay.
Yeah. But this is what I mentioned to you before. To get to really big differences, you'd be subjected to G-forces that would kill you.
Oh, absolutely. Yeah.
Right? But this is really, really nice because it's both kind of an illustration of the similarity to Newton and of the difference. And you see how the difference comes in the time structure, because we've gotten rid of Newtonian absolute time. Clocks can't be measuring absolute time over here. There isn't any absolute time to measure. What they're measuring are the lengths of these trajectories. Now, if we go back here, and just to remind people, because we talked about in the regular twins paradox, so in the regular twins paradox, we can now think of this as...
And what diagram are we looking at again?
We are now looking at a diagram. Oh, we're looking at the circle that I gave you at the beginning, which was Euclidean geometry, but now we're treating it as a diagram in Minkowski spacetime. Okay. And we're going to orient the blue straight line going straight up, and the red line goes straight up, then jogs off, then comes back, and then goes straight up again. So it has this notch that comes out of it. When I ask you in the Euclidean space, you said, oh, the blue line will be shorter than the red one. In Minkowski spacetime, the blue line is longer than the red one. Right? That's why the twin, now if we think of these as the world lines of two twins, here they are together. This one now gets in a rocket, accelerates, goes off that way, comes back, they get back together. The one that went out will be younger. Now, what we mentioned in the first thing is that the constant mistake people make is saying, oh, that's because of the acceleration. It's not, because it's the length. And the reason I put this there's a little dotted blue notch of the same shape as the big red notch for people who can't see this. It's the same shape, but it's shrunk down. So if we say, what is acceleration? Acceleration is curvature or bending of these lines. This blue line is unaccelerated, so you could just do that by drifting. The red line, it's unaccelerated to this point where the two lines come sharply together. Then you need a very sharp accelerator. You turn on your rockets really strong, very briefly, and then you can turn them off and just drift from here to here. Then you turn them on again to come back, sharp bend, you come back, you turn them on a third time to stop yourself. The accelerations are here, where you turn on the rocket, here where you turn on the retro rocket, here where you turn on the rocket again. Those are the accelerations. Those are exactly matched. If I imagine this one who stayed on Earth, just goes out for a very quick jaunt in their rocket, right? They turn on their rockets, go up, immediately turn them on, come back, immediately stop. These are matched acceleration for acceleration, right? The acceleration on the blue trajectory with the little notch is identical to the acceleration on the red trajectory. So if you thought the twins paradox was explained by acceleration, you'd have to say, well, now the twins are going to be the same age. Nope. Because the little notch made almost no difference to the length, and the big notch made a big difference to the length.
I was wondering what that little notch was going to mean.
That's what that little notch is for. It's to explain exactly why anybody, if they reach for acceleration as the explanation for the twins phenomenon, they're wrong. Obviously, this purple thing is constantly accelerating. It's very curvy. I mean, you could imagine it's either being buffeted around or you've got rockets going all the time, causing it to accelerate, essentially.
So this is another crucial misconception.
This is absolutely a crucial misconception.
And am I correct from our last conversation that it was Richard Feynman who made
Yes,
a mistake?
Feynman says it wrong, yes. Feynman talks about this acceleration stuff in the Feynman lectures. I would guess, because so many people read them, and look, there's just plenty of wonderful stuff. And I'm going to give you, when we get to general relativity, I promised you this example that Feynman gives that's beautiful, correct, right on. But his account of the twins, wrong, got it wrong. And I think so many people learn their physics from reading the Feynman lectures because he cares about trying to explain things. Right? He's not just doing calculations. He's not throwing some equations up and saying, okay, calculate this, calculate that. People love that. Mm-hmm. But then when he makes a mistake, they go with it, right? I mean, because they're just learning it. I mean, this is human nature. You're learning from this guy. You're not supposed to be sitting there, you made a mistake. Fine.
Yeah.
But he did. Okay, he's human. That's fine. And when we get to the one that he gets right, you'll see that he understands it there. Okay?
Okay.
Okay, so we've been talking about, again, we're not to general relativity yet. You have to understand special relativity before you get to general relativity. So we've got Newton's spacetime, we've got the special relativistic spacetime. It has this Minkowski structure, it's got a light cone structure, it's got this straight line affine structure. If there's no forces on a particle or an object, it'll travel along a straight line. If it's not traveling along a straight line, there's forces on it. And clocks are ticking off measuring the lengths of these lines in proper time. Okay, so that's, if you just hang with that much, that's going to get us some really interesting results. For those of you waiting at home, you've never seen this. Nobody's ever seen this.
Okay, so nobody's ever seen
Nobody's ever seen this one.
the rightmost poster board.
Yeah, the rightmost poster board we're going to get to in a second. That one I'm very excited about. This one people will have seen. So here's Minkowski space. You notice intuitively the light cones are like nice and lined up and parallel and straight. And this is like Euclidean space. It's isotropic. Every point is like every other point. It's homogeneous. Every point looks like every other point. It's isotropic in a way. It's like Euclidean space, nice, very pretty, lots of symmetries, lots and lots of symmetries in Minkowski spacetime, like there are lots and lots of symmetries in Euclidean space. In Euclidean space, if you move over 3 feet, it looks the same. If you twist your coordinate system, it looks the same, right? All right, now we're going to do the analog of Cartesian coordinates for Minkowski spacetime. They're called Lorentz coordinates. And the Lorentz transformation, which people may have heard of, is a coordinate transformation. It takes you from one set of Lorentz coordinates to another set of Lorentz coordinates. They're just equations that say, if this is the coordinates in this frame, this system, these would be the coordinates in the new one. So let's do this. This is just a Euclidean plane. I can lay down coordinates, Cartesian coordinates on it like that. Or I can move the origin over here, put them down like that. Or I can twist them. And you'll notice when I twist them, and again, people just listening to this, I highly recommend watching it. But you can imagine taking a Cartesian coordinate system and just turning it, right, pivoting it around, say, its origin. So again, in Cartesian coordinates, the blue curves and the red curves always meet at right angles. So if I twist the blues this way, the reds have to twist the same amount to keep it at right angles. So I have an infinite number of different Cartesian coordinate systems I could lay down on this Euclidean space. And then there are systematic ways, if you give me the coordinates of a point in one, to translate them to the other. Those are coordinate transformations. Now, you can do the same thing with Lorentz coordinates. And in Lorentz coordinates, now I'm going to get rid of this disk so we have the light cones. Whenever I draw these light cones, I'm kind of picking, intrinsically picking. So one of the sets of Lorentz coordinates will look just like Cartesian coordinates. When I set up these light cones, there'll be a coordinate that's running just vertically up and one that's running horizontally across, and they meet at right angles. That is a Lorentz coordinate. Now, suppose I want to take this axis, the t-axis, this is now actually time going up here, and I want to twist it over. So I want to go to a new Lorentz coordinate system, but where it's been, as it were, rotated. Now we saw that for Cartesian coordinates, when I rotate this axis this way, the other axis rotates down. And now that minus sign is going to come up again. When the t-axis rotates this way, the x-axis rotates up the other direction, the same amount. Right? Mm-hmm. And it's not too surprising because remember, the light cone itself, when we draw these diagrams this way, the light cone's at a 45-degree angle, which means the light cone is always splitting the difference between the time and the space coordinate. So if I squeeze the time axis over this way, I've got to pull the space axis up the opposite direction, the same amount, so that the light cone still splits the difference. So this is one Lorentz coordinate system. but another Lorentz coordinate system, equally good, just as valid, just as correct. So this pink now is the t coordinate. I've shifted it, twisted it this way, and this blue, light blue, I've shifted up that way. So the Lorentz coordinates in this new Lorentz coordinate system, it no longer looks like they're at right angles. It looks like they're getting squished. But in the geometry, the angle between these two is a right angle. It doesn't look like it because the diagram is Euclidean. But in the geometry, this is a perfectly good Lorentz system. Okay? And if you imagine these two axes getting, if I twist, I kind of push the time coordinate closer and closer and closer to the light cone, and then the space coordinate comes closer and closer to the light cone. In the limit, the light cone, this is going to sound weird to people. I'm just going to say it. I'm not going to explain it. If you're along the light cone, if you have a direction along the light cone, it's orthogonal to itself. It's at right angles to itself. Now, you're going to go, what?
Yeah, what does that mean?
Yeah. But the idea of an angle is well defined here. There's a number, and two of these things are at right angles if that number goes to 0, and it does for the. I mean, we could do that. I mean, that's too much math here. So the point is, this diagram, which is the one I got into, is a single Minkowski spacetime. I'm sorry, it gets a little messy. It's got, I've just superimposed both the Lorentz frames on it. So I have one Lorentz frame. The time coordinate is these blue lines going straight up. The space coordinate are these red lines, dotted lines going horizontally.
And what, just again as a refresher, what is a Lorentz frame?
So these are just a set of coordinates that were discovered by Lorentz. And Lorentz did this, this was before special relativity. This was before 1905. He was just dealing with Maxwellian electrodynamics set in Newtonian spacetime. And what Lorentz realized was that if I write down Maxwell's equations in coordinate form, with respect to these funny coordinates, what he thought were very strange coordinates, they take the same form mathematically. Now, he thought, that's weird, or maybe at best he thought that's convenient, because if I know how to solve them in one set of coordinates, I know how to solve them in the other set of coordinates. And maybe in some situations, this other set of coordinates will be convenient for calculational purposes. But Lorentz didn't go beyond that. He didn't think that this was telling him something deep about space-time itself. He thought of these other Lorentz coordinates, because what's weird about them? What's weird about them is that in every Lorentz coordinate system, there's a time coordinate, a t coordinate. And Lorentz was thinking, as Newton did and as Maxwell did, that there's absolute time. So there are all the events that happen absolutely at the same moment of time. And what we should do is give them all the same t coordinate. In these other Lorentz coordinate systems, because the constant x like this gets tilted, it means all of these get the same t coordinate, even though, as Lorentz would say, but they're happening at different times. Look, this happens first, then later that one, then later that one, then later that one. They're happening at all these different times, but I'm giving them the same t coordinate. So he would think physically that doesn't make much sense, but what the heck? It's just coordinates, right? We can throw down, as we had our funny curved coordinates, you can do whatever you want with the coordinates. So what we have here is the absolute structure is given by the light cone structure. That's going at 45 degrees, the way we draw this. These dotted cones, here's a double here. So the idea, I just got really only 3 things you need to pay attention to here. I've got 3 events. A yellow event, another yellow event right to its future, and a green event off to the side. And they all have light cones associated with them. So for this yellow event, it's this light cone going at 45 degrees. For this yellow event, it's this one. I didn't put the one for the green. Then I've got these different Lorentz coordinates. They're just coordinates thrown on top of it, right? That's why I put them on these acetates. They're not really there.
Right.
one set of Lorentz coordinates chops, as it were, the equal t surfaces chop horizontally. All of these events have the same time coordinate. In the other one, they don't, they chop at this angle, this pink angle. These all have the same t prime coordinate. So you might say they count as simultaneous in that reference frame, but that's a funny thing to say. They just have the same t coordinate. They have the same, it's a coordinate dependent. We made at the beginning, what I was trying to hammer home was the difference between physical structure and mere coordinate dependent structure. So what can we say absolutely? What will be true in all the Lorentz frames? Well, all the Lorentz frames will agree that this yellow event happened before that one. In every single one of them, the t coordinate given to that one will be less than the t coordinate given to that one. So the time order between these events is objective. But between the yellow and the green, you'll notice that if I chop up time horizontally, then the order is first yellow, then green, then second yellow, because you think of time doing this. If I chop it up in the pink way, another perfectly good Lorentz frame, then it says, oh no, the green one comes first, then the first yellow, then the second yellow, right? They agree that the first yellow comes before the second yellow. They disagree about the order that the green one is. Notice the green one is at what we call space-like separation from the yellow ones, meaning it lies outside their light cones. Here's the light cone of this yellow, the green is outside. Here's the light cone of this yellow, the green is outside. When two events are at space-like separation, they have no objective time order in relativity. There's no fact, physical fact about which came first. There'll be some Lorentz frames in which the A comes first, some in which B comes first. There'll be one in which they happen at the same moment. There's a Lorentz frame that chops this way that makes them simultaneous. Those are not physical facts. Those are just coordinate, fluff.
No, I think that the idea of using the coordinate systems as acetates to show that they're not really there, they're just impositions, is a really nice move.
Right. And it's hard. I thought I could hold up two acetates at the same time. That's too hard. So that's why this is the only one where I printed two different coordinate systems on it. So you can look and see how they differ.
Right.
And so each coordinate system will assign a t difference and an x difference. You can think of those as coordinate time and coordinate space. And those will be very different. They will agree about these invariant intervals. They'll agree about proper time. They'll agree about the light cones. All of that's objective. Okay? Now we're going to get to the one I'm really proud of. Now, remember we said clocks measure proper time. Proper time is an absolute objective measure of the lengths of these curves. Right? Clocks measure proper time along their trajectories. Now, what I have here is Minkowski spacetime. Again, we're just in special relativity. We're not even mentioned general relativity yet. I've got three observers here. You'll notice these curves, there's a blue hyperbola, there's a purple hyperbola, and there's this red line which goes straight up, then suddenly bends. Then it goes out here, it bends again, it bends again. You can't see the bends. You can't see them on the diagram, but they're there. I'll explain who these people are. This one you've never heard of, the red one, okay? What's going on? Well, first of all, you notice these observers, just if you focus on the blue and the purple, they're this hyperbole, they're obviously not straight, right? They're bent, they're accelerated. In fact, these are observers who are each being constantly accelerated. They have rockets on, and the rockets are accelerating them in that direction toward you.
Okay.
Okay, so they're kind of coming this way, and then they get this far, and then they go off that way toward you. This one, the blue one, much more sharply, much stronger rockets than the purple one. And you could imagine having, as it were, shallower and shallower of these hyperbolae that get less and less curved. In fact, all of these hyperbolae are are defined relative to this point. And as we get sharper and sharper, you would have one coming in like that, one coming in like that. Okay, now it might look like on this diagram, remember it's a Euclidean diagram, so you're going to be a little confused about this. It looks like, oh, these blue trajectory is really curved here, but as you get further and further out, it gets straighter and straighter, but it doesn't. These have constant curvature in this geometry. This is a constant acceleration. You've got your rockets firing all the time. You have stronger rockets on the blue than on the purple, okay? So let's just, now what we can do is measure these trajectories in proper time. And I'm going to put pins in for the ticks of the clocks.
Okay.
Okay? Now, it's a little tricky here. I'll get to the red one at the end. So I'm going to put a push pin here.
So you're putting a yellow push pin in the
No, I'm putting the blue. I'm putting a blue in the blue. Okay? The yellow one I'm not going to need. All right, so he ticks once. And if you just measure this in, say, minutes, the way I've done it, I'm going to have them tick at 30-second intervals because that just works on this diagram. So I've got it marked here. The next tick would come here, which is just, you can't quite see, it's slightly above what would be 0.5 on this axis. So this vertical axis is a Lorentz frame, and these numbers are in the coordinates of that Lorentz frame. It ticks at 30 seconds, as it were, only slightly after 30 seconds according to that frame.
Okay.
The next tick comes here, and now the second tick in the Lorentz frame, the minute mark would be here, and you'll note now it really is kind of delayed more. Let's put in the next tick would be here. Now you're starting to see it's on this diagram, it looks like it's getting longer and longer periods of time. But I seem to have run out of blue, so I'll switch to green. I'll just put these ticks in.
And again, just what does the increasing distance between the push pins represent?
That is an artifact of this diagram. Okay. In the intrinsic geometry, and this is the point, in the intrinsic geometry, the length of that segment of the arc is exactly the same as the length of that segment, is exactly the same as the length of that segment. These are all identical. And this clock will tick forever, marking off, in this diagram, marking off points along this hyperbola. But the tick marks in this diagram will get longer and longer, will get farther and farther apart. What does that illustrate? If I describe this situation from the point of view of this Lorentz frame, the one that's looks like a Cartesian coordinate system here, it's going to say, oh, this clock is ticking ever more slowly. It's taking more of my coordinate time for it to get to its next tick. And because it's constantly accelerating, it's going, as it were, in this frame, you'd say it's going closer and closer to the speed of light. It's slowing down more and more. It'll tick forever, right? It'll never stop. But it, as described from this Lorentz frame, represented by the edges of this thing, the ticking will get slower and slower according to its t coordinate. Now, it's not really getting slower. The clock is just measuring out the objective length of these curves. Okay? If we were ticking off the clock that would be going up this diagram here is ticking at all of these marks. So there's 0, 0.51, 1.52, 2.53, 3.54, 4. So you can imagine the same clock, identically built clock, is going to be ticking regularly, tick, 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 tick along there. This one's doing that. Okay? Mm-hmm. This one is more highly accelerated. Now let's look at the purple one. The purple one is not as curved. It's not as accelerated. Its rockets are not firing as strong. And it will also, as it were, appear to be delayed, it's going to tick, as it were, closer to the rate. I'll pick that up later. Closer to the rate as seen on this diagram that the one does here. Now I have to say something very careful here. This is the first tick of the blue clock. I'm now going to put a clock along this trajectory. That clock is going to be measuring the length of this trajectory.
The purple.
The purple trajectory. You might say, well, shouldn't you synchronize them? And the answer is nothing counts as synchronizing them because we don't have Newtonian absolute simultaneity anymore.
Right.
So I have to put a tick somewhere over here at space-like separation from here. I could kind of put it anywhere. I'm going to pick this point because it's just convenient, but it doesn't mean anything. So I'm just going to have the first tick of this clock here. And now I've got these marked. And now you'll just see where it ticks. So it ticks, the next one is here. The next one. And you'll see, just looking at the diagram, how you would say it's ticking faster, right?
Right.
Maybe that one was marked. This one actually must go up somewhat bit higher. Like that, then like this. I mean, you can just, looking at it, say, well, yeah. Notice it's less accelerated. We always said the straight lines are the longest ones. So the ticking is fastest along the straight one. This one has no forces on it. This is an inertial clock. It is just floating through empty space. These clocks are on rockets. Ticks here. Ticks here. Okay.
So because the purple line is closer to flat than the blue line, the ticks are closer together.
Right. Okay. And again, that clock will tick forever. In fact, in the intrinsic geometry, each of these little sections of arc are exactly like every other one. They're all identical. Okay? Remember this. No, again, this is in special relativity. This is a more accelerated clock. This is a less accelerated clock. The more accelerated clock is, as it were, ticking slower. The less accelerated clock is, as it were, ticking faster. Because we're going to see that in general relativity. People don't understand. You already see it in special relativity. Now I'm going to give you the one nobody's ever seen before. You'll appreciate this. The Zenonian observer.
The Zenonian.
The Zenonian.
As in Zeno.
As in Zeno.
Okay.
Exciting.
Okay. Now, the first tick of the Zenonian observer, I mean, I'll just kind of put it here. These guys really, they start out at the origin there, so we can really synchronize them, right? Those two clocks are right next to each other, red and blue, right next to each other here. We set them to 0 when they're next to each other. As I said, to set this one to 0, I had to make an arbitrary choice, but here they're right next to each other. It's not arbitrary. For the first minute, this one doesn't accelerate at all. It just travels inertially along this trajectory.
The Zenonian.
The Zenonian. For the first minute, it's unaccelerated. And so the ticks go as these little marks here. And there'll be 2 of them, because remember, it's ticking at a rate of 30 seconds. So there'll be one there, there'll be one there, okay? You'll notice the blue is pushing up a little. Again, the curved ones are shorter.
Right.
Now, at this 1 minute mark, we're going to give the Zenonian observer a really strong push, an instantaneous, very sharp acceleration. Okay, so he's straight. It's like we had on this diagram when we talked about the twins, that the red twin is just going on inertially, and then he gets in, turns on his rockets here, and then he turns them off and just drifts. And then here the rockets come on, and then he just drifts. This is a very strong sudden acceleration, right, that we indicate as a sharp bend.
Right.
So the way to think about this is, at this point, we're going to give him a sudden acceleration, and we're going to move him up to a speed where, according to our original reference frame, his clocks are now ticking at half the rate. So now instead of ticking once every 30 seconds, they're ticking once every minute. Okay? And we're going to let that go on for 2 minutes. So at 1 minute, the Zenonian will tick. And then well, this was 1 minute. At 2 minutes, he'll tick. At 3 minutes, he'll tick. But you'll notice we gave him such a sharp acceleration. You'll notice some things are happening. One is, even though for the first minute he was just sitting there and blue and purple were moving away, he's already gone past blue. He's caught up to blue and shot past blue. And you'll see up here he's going to shoot past purple as well. He's going to be the one going fastest. Okay, so set to 0. First tick, second tick, third tick, fourth tick. Now we're going to give him another shove. And again, his clock's going to slow down by a factor of 2. So whereas here it took 1 minute in this frame to go from tick to tick, now it's going to take 2.
Mm-hmm.
But we're not going to allow that to go on. We're only going to allow these accelerations. We're not going to keep expanding the amount of time so he gets to the next tick. So the other way to say it is, in the first minute, you're going to read off a minute of time. In the second minute, you're going to read off half a minute. In the next one, a quarter of a minute. In the next one, an eighth of a minute. In the next one, a 16th of a minute. We can always keep pushing him and accelerating him. And as it were, slowing his clock down with respect to this frame. Now, I think you'll understand why he's Zenonian. Because if you add up 2, which you get in the first minute,
Mm-hmm.
then you get 1 in the next minute. Then you get a half. I mean, this is actually the half. Then you get a quarter. Then you get an eighth. He's never going to get, right? This is a trajectory of finite proper time.
Mm.
He's never going to get to an unbounded amount of time.
Right.
I mean, I'd have to figure out the way I have this set up. I think he never gets to 2 minutes, or anyway, he never gets to 4 minutes. He's there all the time. He's in Minkowski spacetime. He doesn't disappear. His trajectory just keeps getting these shoves. Now, you don't see the shoves here because once you get the differences become hard to see in this diagram. But you can see conceptually I can do that, right? I can have him tick the amount of time between here and here is 1, then a half, then a quarter, then an eighth, then a 16th. You never get to 2. So that is a trajectory of finite proper time. He will never see the clock tick, 4, I think. Or, if these are, I would have to think about exactly, but, he'll never see it. It'll never get there.
Mm-hmm.
So all of this is happening in Minkowski spacetime. And in a way, it shouldn't surprise you. Why? Because we know the proper time. Notice what's happening. Here's a light ray going out along a light cone. First of all, you notice the blue, the purple, and the red. None of these observers will ever intersect that. Their trajectories will never hit it. Furthermore, the red trajectory is getting closer and closer to a light ray. And we know the length of the light ray is 0. So the length is getting shorter and shorter and shorter. So they're actually trajectories. They don't end. There's always more of it.
Mm-hmm.
There's no singularity, but they're of only finite proper time. Okay?
Yeah.
Now that is going to happen with black holes.
Okay.
So this is what I'm trying to indicate here is I'm giving you some behavior that happens with black holes. And because they're black holes and black holes only come up in general relativity, people think, oh, this is part of general relativity. No, this is special relativity here. This is all special relativity. There are inextendable time-like curves that have only finite proper time lengths. And if you were an observer, or if you had a clock, it would never tick beyond a certain point. In the same way that Zeno says the arrow will never get to the wall, right? Half, 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 half. But in this case, we're doing it with the actual metrical distance.
The Zenonian observer, I like that name.
Yeah. Now, the other thing to notice about all these observers, again, these observers are not Zenonian. Their clocks keep ticking forever. There's no limit. But notice, none of these observers, none of these trajectories ever intersect this light ray. So if at this point right here, and I'm sorry, I don't know quite how to describe it for those who can't see this, if a light signal were sent out from this point, none of these observers would ever receive it. They'd never see it. Why? Because their trajectories never intersect that light ray. Mm-hmm. So this forms a kind of horizon to what these observers will ever see. But again, we're not in general relativity. You've heard about event horizons. You've heard about all this stuff with black holes. We're not talking about black holes. We're just talking about plain old flat Minkowski spacetime. There are events that will happen in this universe that none of these observers could possibly become aware of because they will never intersect the future light cone. Now, I've gone to a lot of trouble to do this in special relativity because when we get to general relativity in black holes, you're going to see exactly the same behavior. And what you should realize when you think it through is that that behavior was already there in special relativity. It's nothing about general relativity, really. It's about this kind of funny pseudo-Riemannian metrical structure and how it works. All right, now, the last thing we're going to do to illustrate, when I said at the beginning, there's a lot of confusion about relativity, and there's a lot of confusion among the experts about relativity, even special relativity, which is a pretty simple theory. I'm going to give this example that John Bell gives. John Bell writes a wonderful paper called How to Teach Special Relativity. And this is a quote from that paper. So we're going to do that, and then I'll actually talk about, show you how this works and show you, and then we'll be done with special relativity. Having done this, general relativity is going to go like that. So all of this work is really going to pay off.
Okay.
All right, so let me just read this. So for people at home, this is again, if you want to get Bell's book, Speakable and Unspeakable in Quantum Mechanics, it's almost all about quantum mechanics, but there's this paper there called How to Teach Special Relativity, where he's complaining about how people teach special relativity, because he says they end up not understanding it. So here's just the quote from the book. He says, "You might try the experiment of confronting your students with the following situation. 3 small spaceships, A, B, and C, drift freely in a region remote from all other matter." So that they're just following these straight lines, right? That's what we said. That's free motion, inertial motion, following these straight lines. Without rotation, right? So they're not spinning. And without relative motion, with B and C equidistant from A. So A's in the middle, B and C are on the side. They're equally far away, and they're just drifting, and they're not moving with respect to each other. On reception of a signal from A, the motors of B and C are ignited and they accelerate gently. So these people are accelerating very strongly. These are going to be done more gently. Let ships B and C be identical and have identical acceleration programs. Then, as reckoned by an observer in A, they will have at every moment the same velocity and so remain displaced one from the other by a fixed distance. So you imagine these 2 rockets, identical rockets, are both heading in the same direction. One's in front of the other. They start off on getting this light signal from A, and they accelerate. According to A, their acceleration programs are the same, so they maintain a constant distance between them. Okay? We're going to see this in a second. Suppose that a fragile thread is tied initially between projections from B and C. If it is just long enough to span the required distance initially, then as the rockets speed up, it will become too short because of its need to Fitzgerald contract and must finally break. Now, let me explain the Fitzgerald contraction. So we've talked a lot about time dilation effects and clocks. There's this other thing called the Lorentz contraction, which was an attempt to explain the Michelson-Morley experiment, which we could go back to if we want to. But basically, the way it's always said is, as objects go faster, they shrink in the direction of motion. They contract in the direction of motion. Okay, they get shorter. This was supposed to explain the null result. So as these rockets go faster and faster, there's going to be this tendency for the thread to want to Fitzgerald contract. But the ends of the thread are pegged to these two rockets that are at constant distance from each other, right? So he says, as the rockets speed up, it'll become too short because of its need to Fitzgerald contract and must finally break. It must break when, at a sufficiently high velocity, the artificial prevention of the natural contraction imposes intolerable stress. So do you get the basic physics here? It's almost as if you would wet the string and it was contracting as it dried, right? It was shrinking the way a sweater shrinks, all right? So the thread is trying to contract. These rockets are keeping it from contracting. Eventually, the stress builds up and the string breaks, okay? Mm-hmm. Is this really what's going to happen? Will the thread really break? Now, notice the beautiful, beautiful thing about this. It's a question about an unambiguous physical effect. The string breaks or the string doesn't break. Mm-hmm. Question: does special relativity predict the string will break? So here's Bell. Bell worked at CERN. This old problem came up for discussion once in the CERN canteen. A distinguished experimental physicist refused to accept that the thread would break and regarded my assertion that indeed it would as a personal misrepresentation of special relativity. Okay, so here's Bell arguing with another physicist at CERN about what special relativity says in this case, implies. We decided to appeal to the CERN theory division for arbitration. You might say, oh, well, it's an experimentalist. Okay, let's go to the theory division. And made a not very systematic canvas of opinion in it. There emerged a clear consensus the thread would not break. So these are top theoretical physicists at CERN, given a very concrete physical question, according to special relativity, will the string break? Of course, many people who give this wrong answer at first get the right answer on further reflection, right? They were wrong. They didn't understand the theory. Usually they feel obliged to work out how things look to observers B or C. They find that B, for example, sees C drifting further and further behind so that a given piece of thread can no longer span the distance. It's only after working this out, and perhaps only with a residual feeling of unease, that people accept a conclusion that is perfectly trivial in terms of A's account of things. Now remember, A doesn't accelerate at all. A just sits there, sends this signal out to B and C that sets them off. And A, of the three of them, is the only one that stays in a single Lorentz frame. And in that frame, the rockets are always a constant distance apart, but they're going faster and faster. And he says, look, as they go faster, they'll have to Lorentz, the string will have to Lorentz contract, it'll break. That's the whole argument. As it goes faster, the string will have to contract, it'll break. So that people accept a conclusion that is perfectly trivial in terms of A's account of things, including the Fitzgerald contraction. It's my impression that those with a more classical education, knowing something of the reasoning of Larmor, Lorentz, and Poincaré, as well as that of Einstein, have stronger and sounder instincts. I'll try and sketch here a simplified version of the Larmor, Lorentz, Poincaré approach that some students might find helpful, and then you have this whole article about teaching special relativity in the way he thinks it should be taught. So that for a case like this, you don't have to calculate. You think. And he says, no, this if you're thinking of this from the point of view of observer A, these rockets are going faster and faster. The Lorentz contraction will, the internal structure of that string will want to contract. And because the ends are pegged at a constant distance apart, it can't. It'll eventually break. Okay?
Mm-hmm.
And the reason I wanted to go through this is that this is another example. This is not, you know, amateurs or whatever misunderstanding relativity. This is the theoretical division at CERN being given a pretty simple question about special relativity and offhand getting it wrong. Now, as Bell says, don't get too upset. If they do the calculation, it'll come out right. If they shut up and calculate, they'll figure out it'll break.
Mm-hmm.
But his complaint is that you shouldn't have to do the calculation. You should be able to think through, from the point of view of a single Lorentz frame, what must happen physically. Now, it's this Fitzgerald contraction that breaks the thread that is the very complicated thing to explain. This is why rods are hard. This is why rods are complicated. They're made up of all these little pieces, and the pieces are in a solid, and the solid is being held together by electromagnetic forces, and electromagnetism is being described by Maxwell's equations. And all of this gets very complicated. Now, Bell goes through in a very simplified way of showing how these effects would occur, as told from a certain frame of reference. This is a space-time diagram. This is the last one we're going to do in special relativity. It's going to explain a lot of things that people talk about the Lorentz contraction and things getting shorter and blah, 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 okay? We're going to then leave that behind because I said meter sticks are complicated. We want to stay away from them. We want to do light, we want to do clocks, we want to do gyroscopes. Here's a couple things. So on this side, and I've covered it up, is the situation Bell just get. Here's observer A. You'll notice observer A's trajectory is straight. Observer A is completely unaccelerated. Observer A is situated equidistant from B and C. At the beginning, they're also unaccelerated. At a certain point, A sends out a light signal. So it's going at 45 degrees along the light cones. And when the light signal gets to B and C, they turn on their rockets. Rockets are identical. When they're so the trajectory of this rocket will look just like the trajectory of this rocket moved over in this diagram. They will maintain, from this point of view, a constant distance. This yellow represents the thread that's tied between them. And the question is, will the thread break? That's, the correct answer is hidden at this point. Before we get to that, because we actually kind of already know the answer, because I read, we know the correct answer. Let's talk about similar situations. People talk about the Lorentz contraction. If I'm in a car, if I drive it fast, it'll contract. Spatially, right? It'll shrink.
Mm-hmm.
And people always say, but how can that be? Because, again, all motion is relative. Suppose I have a car in a tunnel, and if I can park the car in the tunnel, the front end of the car exactly is at the size of the beginning of the tunnel and the back end at the end. So if I park them next to each other, so they're not in relative motion, they're the same size, right? Now I go out, I turn the car around, I speed it up, I run it through the tunnel. Now someone says, well, from the point of view of the tunnel, that is described in the tunnel's Lorentz frame, the car is moving. And if the car is moving, it must shrink. And if it shrinks, then it must fit now completely within the tunnel, right?
Mm-hmm.
But wait, what if I'm the driver of the car? Once I get it up to speed, according to me, it's the tunnel that's moving. So according to me, it's the tunnel that shrinks. So according to me, I'm now longer than the tunnel. How can that be? How can those descriptions both be true? How can it both be the case that the car is shorter than the tunnel and longer than the tunnel, right? So this is the kind of puzzle people have in their heads. And what you have to do to resolve that puzzle is to understand that the notion of whether the car or the tunnel is longer or the same size is not an objective question. It's a frame-dependent question. It's a coordinate system dependent question. What I've done on this side of this diagram, this side is Bell's problem with the rockets and the string. This side is the car and the tunnel, and then the car. They also do this with a car in a garage. You've probably heard this. You say, oh, you've got a car. It's too big to go into a garage. All you got to do is speed it up fast enough. And relativistically, it'll shrink, and then you can fit it in the garage, right? And close the door behind it. Well, doesn't that show it really did shrink? But how can that be? Because that suggests that there's a fact about what's moving and what isn't. Okay, so what I've done is I've indicated on this side of the diagram we've got the car in the tunnel and we've got the car in the garage, and on this side we've got Bell's rocket. All right, let me just go through these and then we'll be done with special relativity. So this red part, just if you're I'm sorry if you're just listening. There's a red long thin rectangle going vertically up on this diagram. That represents the tunnel, and there's a thinner looking blue parallelogram that's going to the side that represents the car, okay? And this is just a space-time diagram. So the tunnel is all of this region, red region, the car is all of this blue region, and the green is going to be the garage. The garage, by the way, has a very, very strong back wall, so that when the front of the car gets to that wall, it stops.
Okay.
Okay? And okay, let's not worry about the garage yet. Let's just look at the tunnel. All right, so here's the car going through the tunnel. Now, I claim if the car and the tunnel were not in relative motion, if you just park the car in the tunnel, they're the same length. But now the car and the tunnel are in relative motion. They're moving with respect to each other. So which is longer than which? Well, to ask that question, you're actually implicitly using a standard of absolute simultaneity. So in one Lorentz frame, in the Lorentz frame associated with the tunnel, the equal t surfaces cut horizontally on this diagram. They cut exactly horizontally. And so we can find a spot. Oh, maybe if I can indicate it this way. We can find a spot, an instant of time, right there, where you'll notice, according to that frame of reference, the front end of the car is not yet out of the tunnel and the back end of the car is inside the tunnel. Mm-hmm. So in that frame of reference, you would say, the car is now shorter than the tunnel. But if we think about how the Lorentz frame associated with the car, we've tipped the t-axis this way. We've got to tip the x-axis up. Remember, we tip one this way, we tip this up. Now, if we go into the reference frame of the car, we can also find a moment, here's one, where by that simultaneity, the back end of the car has not yet entered the tunnel and the front end of the car is already out of the tunnel.
Right.
So according to that frame of reference, the car is longer than the tunnel. Do they contradict each other? No, because this cut and that cut are completely different cuts. Those are cuts of equal t, and t is just a coordinate. It's not physical. There is no absolute simultaneity, so there's no absolute fact about who's longer than who. You have to see that Lorentz contraction, that kind of it, as a coordinate-dependent effect. It's not a physical effect. Now, there was a physical effect that had to occur when the car, if it was originally parked and was the same length and then drove way over here and then came back. In all that process, stuff happened and it was accelerating and all kinds of things were happening internally. We can't even represent that. But here you understand there is no objective fact about which is longer than which. Why? Because that judgment depends on fixing a notion of simultaneity, and different frames of reference will differ about that. Now, what about the car that drives into the tunnel? You say, well, objectively, of course, the car must be shorter than the garage because you can drive the car in, it'll crash, but you can drive it in and then close the door behind it. Mm-hmm. Well, that's indicated here. Here's the crash point. This red line is light coming off of the crash. Now, what do we know? We know that in Maxwellian electrodynamics, nothing goes faster than light. So the back end of the car can't possibly, as it were, be affected by this crash until at least there's been enough time for light to get to it, for the shock wave to get to it. Shock wave can't go faster than light.
Right.
So here's the crash. And of course, the back end of the car has to keep going until at least there where the light cone hits it. And by that time, the car is crushed.
Right.
Yeah, it'll fit in the garage.
Yeah.
Doesn't show it was really shorter than the garage. I mean, it's shorter than the garage after it's crushed. It doesn't show that in any objective sense, it was shorter than it when it went in. Okay? And then you can just work out all the details. Now, the answer, and so that's the answer to Bell's thing too. I mean, I hid that, but will the string break or not? I mean, there's just a fact there, right? There's just a fact. One thing you cannot say, and I just have to repeat this for a reason, it seems so stupid to have to say it, but I have to say it. One thing you cannot say is, oh, there's a principle of relativistic complementarity such that according to observer A, the string breaks, and according to B and C, it doesn't, or something like that. That makes no sense at all.
I imagine you have a particular
I have a
person in
very
mind.
particular thing in mind.
Yeah.
Those are just contradictory descriptions. The string breaks or it doesn't break, for God's sake.
Is this Lenny?
Yes, it is.
Okay.
And you can't get rid of a contradiction by wheeling in the word complementarity. Okay? Either the string breaks or it doesn't break. The brilliance of Bell was to just ask that question. Does the string break or does it not break? A bunch of people in the theoretical division at CERN incorrectly said it would not break, which means they don't really understand the theory. Now, again, he says, okay, they did the calculations and it was okay. But understanding can allow you to circumvent the calculations. And even if you can do the calculations right, who cares? Right? I mean, that's not what I care about. I don't care about calculating something correctly. I care about understanding it. And even special relativity, and we even touched general relativity. We're going to do that. We're going to have a intermission. And then do general relativity. Oh, it's going to go real quick. Surprisingly quick, because we've spent so much time on special relativity. If you don't understand it, you're going to get yourself into a mess. If you mix up objective physical things with merely coordinate dependent things, you're going to get into a mess. And all of that's illustrated here. This thing, this diagram, which I got off the web, is Minkowski spacetime. So I had this thing of Minkowski spacetime that I did with light cones that look like this, and this would go on forever. It's infinite. That light cone structure, that conformal structure, we say is central to relativity. And this is a diagram that was created by, this kind of diagram created by Roger Penrose, called a Penrose diagram. And you'll see the light cone structure is indicated on the diagram here. But even though this is the Penrose diagram of all of Minkowski spacetime, even though Minkowski spacetime is infinite in all directions, in this diagram, it's gotten shrunk down to a finite diamond here. All right, so what we have here are the light cones. We see the light cones and they always look at 45 degrees everywhere. So we can follow light easily on this diagram. Light will always originate at scry minus, along here or along here, and it'll end up along scry plus if it's in a vacuum. It'll just travel along a straight 45-degree angle. For the time-like trajectories, if you're an inertial observer, if you're never accelerated, you'll start at the bottom at time-like, past time-like infinity and end up at the top at time-like future infinity. But not every observer will end up here. And we know that because remember, we looked at our Rindler observers that curved off, and actually, yes, they had infinite proper time, and our Zenonian observer that had only finite proper time. And we saw there are certain light cones, they never intersect. So that means those trajectories have to bend off like this and end up at scry plus. So they don't get up here. So you can't, there's a bunch of things you can't read off of this diagram at all. You can't read how much time passes. You can't read the length. It's just the conformal structure, the light cone structure. But that tells you very interesting things about who can see what. Okay, what you can see from any point, what observers can see anything ever. Do they intersect the future light cone or not? So you can read a lot of that off this. And when we get to black holes, the easy way to understand a black hole, one way is through a Penrose diagram like this. It has the convention that the light always goes at 45 degrees in the diagram. We're going to look at another way of depicting a black hole, which has a different convention. It looks different. We're going to compare them. So I just wanted to do that. The other thing I forgot about that I just want to mention, we talked about in Euclidean geometry, we have Cartesian coordinates. They correspond to Lorentz coordinates. And then we said in Euclidean geometry, you also have these polar coordinates, right? So you have circles and straight lines like the dartboard. Well, what happens in Minkowski geometry? Well, the equivalent to polar coordinates are what are called Rindler coordinates. Now I'm going to pause for a minute to say Rindler is the luckiest guy in the universe, because Rindler did his work in the 60s, and these are called Rindler coordinates, and Einstein was using them in 1908. And lots of other people were using them in the 20s and I mean, Rindler did not invent these coordinates,
Right.
but somehow he managed to stick his name on them.
Very lucky guy.
Applying them into general relativity. In special relativity, they were used from the beginning. Why? They're the analog of polar coordinates. And what happens when you put that minus sign in is the circles in the polar coordinates become hyperbole. And kind of sines become hyperbolic sines and cosines become hyperbolic cosines. Again, it's very systematic. Anyway, so this is what Rindler coordinates look like. And you'll notice they don't cover the whole thing. I mean, you've got these blue coordinates. These are like the circles in polar coordinates, but now they're these hyperbole. These are our Rindler observers, because they're on constant, on coordinate curves of the Rindler frame. And the time coordinate is doing this. The time coordinate is twisting. So just as in polar coordinates, the middle point doesn't have a theta, this one doesn't have a time. All the times, as it were, meet here. And furthermore, if you think of this as a seesaw, as time goes this direction on this side, it goes the other direction on the other side. People get very confused about that, but that's just what these coordinates do. They kind of don't, the coordinates don't extend here and here. So there are all kinds of coordinate singularities. It's not a great coordinate system, but it is at right angles. All of these red lines meet all the blue lines at right angles. So it's very convenient for some purposes. Certainly convenient if you're trying to describe our Rindler observer, who's just traveling along one of these constantly accelerated curves. Good. Now we've done all that, and now we're going to get to general relativity. As I said at the last time, Einstein had only two theories to worry about, starting at the beginning of the 20th century. Maxwellian electrodynamics, that's taken care of by special relativity. Then there was Newtonian gravity. And we saw at the very beginning a 10-year gap. We saw Einstein say one reason there was this gap was he was confused about coordinates. There were other reasons. The reasons that many people give about why it was hard to get a relativistic theory of gravity starting from Newton are 100% wrong. One of the people, I mean, I don't have that here, but I have this here. One of the people who says a wrong thing about this, and I'll just read it here, is Steven Weinberg. I'm going to have a quote from him later, but here's what Weinberg says in explaining the world. He says, in Newton's theory, the gravitational force at a given point in a given time depends on the positions of all masses at the same time. So a sudden change of any of those positions, such as a flare on the surface of the sun, produces an instantaneous change in the gravitational forces everywhere. So Weinberg's thinking that according to Newton, gravity acts instantaneously at a distance. This was in conflict with the principle of Einstein's 1905 special theory of relativity that no influence can travel faster than light. This pointed to a clear need to seek a modified theory of gravitation. In Einstein's general theory, a sudden change in the position of a mass will produce a change in the gravitational field in the immediate neighborhood of the mass, which then propagates at the speed of light to greater distances. Now, the first point I want to make is no, the problem was not that Newtonian gravity was instantaneous. That would be a problem because in relativity, nothing counts as instantaneous. There's no simultaneity anymore. That wasn't the problem. First of all, Newton himself would never have said that gravity was instantaneous. Newton thought gravity was somehow produced by some particles. They would have gone at some speed. He didn't know what they were. The very point in Principia where he says famously, hypothesis non fingo, right? I frame no hypothesis, is he's shown you various facts he thinks he can derive about gravity from the phenomena. And he says, I don't want to do more than that. I don't want to just make up fairy stories. I'm not gonna make a guess about the cause of gravity. But we know from his letters he thought it was caused by a particle. We know if you'd asked Newton, look, wouldn't it take some time if there was a solar flare for the gravitational effect to get to Earth? He'd say, sure, of course, some particles have to get here. Why didn't he care about that gap? Because he thought that speed was very fast relative to the speeds of the planets. The planetary orbits were more or less quasi-stationary, so the transit speed wouldn't make a noticeable difference. It would make a theoretical small difference, but not a noticeable one. He didn't care. And furthermore, the claim that there was a problem there is just ridiculous because special relativity is a relativistic theory of electromagnetic theory. And in electromagnetic theory, as we'll see, the Coulomb force looks just like the Newtonian gravitational force. It just formally looks identical. So if there was really a problem with Newtonian gravity, there would have been a problem with electromagnetic theory, and there wasn't. Okay, so the two actual existing theories that they had, beginning of the 20th century, Maxwellian electrodynamic theory, Newtonian gravity. Now, Einstein needs to account for gravitational effects. They're known, they've been observed for thousands of years, lots of data. You went through Ptolemy, you went through Copernicus, you got to Kepler, you now know the planetary orbits are these ellipses, and you've got Kepler's laws and all this stuff. I said in our first interview, when we started Newton's bucket, I said Newton's bucket, you could argue, is the most important experiment in the history of physics. And the only competitor I can think of is the one we're about to do.
Okay, awesome.
So we're going to do it, and then this is a metal coin. Hold that. Sort of.
Metal coin.
A metal disc.
Metal disc.
Right? Somewhat dense. This is, as you will see, is a little snipped out piece of a feather.
Yeah.
Now, if I were to ask you to hold those out in front of you and let them go at the same time, first of all, what would your prediction be about how they would fall?
That this one would fall faster.
All right, give it a shot and see what happens. Yep.
Yes.
Right?
I should have said that the coin will fall faster.
Yes,
yeah.
that the coin will fall faster. And it hit the ground. It made a sound as the feather was fluttering down. Mm-hmm. We know that it's gravity that accounts for why either of them goes down when you let go of them, mm-hmm. right? So somehow this is a gravitational effect. Aristotle famously, on the basis presumably of this kind of observation, said, heavier things fall faster. Which wouldn't surprise you because you lift a heavier thing, you'd say, it's heavier. There's a stronger force on it going down. Heavier things should fall faster than lighter things. Now, Galileo, because of course he really had to undermine a lot of Newtonian physics to do what he was doing, said this is all a mistake. Now, he had interesting kind of a priori arguments about why it just is impossible. It's kind of internally self-contradictory to say that heavier items fall faster than lighter items. We could go through if you want to. But here's the passage from the Two New Sciences, where he talks about this. Salviati. I seriously doubt that, so if you'll remember, those of you who don't know, the two new sciences is Galileo's discussion of two new sciences. It's like his other famous book is on the two chief world systems, which was about arguing for Copernicus against Ptolemy. And you have the same characters. Simplicio represents an Aristotelian, a kind of scholastic Aristotelian who doesn't do any experiments and gets all of his physics and all of his natural science by reading Aristotle. And Salviati is supposed to be the neutral observer in the debate, and Sagredo stands in for Galileo. So Salviati, I seriously doubt that Aristotle ever tested whether it is true that two stones, one 10 times as heavy as the other, both released at the same instant, to fall from a height of, say, 100 brachia, differed so much in their speeds that upon the arrival of the larger stone upon the ground, the other would be found to have descended no more than 10 brachia. So you see, the idea is that he's reading Aristotle as saying the 10 times heavier stone will fall 10 times faster. So when the heavier one hits the ground at 100 brachia, the other one will have only fallen 10. Simplicio. But it seemed from his words, Aristotle, that he appears to have tested this, for he says, quote, "We see the heavier." Now this "we see" suggests that he had made the experiment. A very careful reading of Aristotle. Sagredo. But I, Simplicio, who have made the test, assure you that a cannonball that weighs 100 pounds or 200 or even more does not anticipate by even one span the arrival on the ground of a musket ball not more than half an ounce, both coming from a height of 200 brachia. So these are fictional characters, but the claim is Sagredo did this experiment. People may have heard of this as Galileo dropping a heavy light object off the Leaning Tower of Pisa. There's all kinds of historical debate whether he actually dropped them off the Leaning Tower of Pisa and whether there was anybody to watch and so on. Apparently that's not settled. But there's a pretty clear direct implication here that Galileo did take a relatively heavy cannonball and a light musket ball, drop them, and notice they didn't hit exactly together, but they hit much more closely together than Aristotle's theory would allow. Okay? So then you say, but what about the feather, right? I mean, and this is the kind of thing in the history of science that's very important to understand. When you start theorizing, you start with phenomena. And you make a choice among the phenomena because different phenomena will be suggestive in different ways. This phenomenon, I'm dropping them again, and again, the feather just floats down, absolutely suggests that the heavier object falls faster. The cannonball looks like it's going the other way, while the cannonball and the musket ball, they're falling pretty much the same. So how do we, where do you start? Which phenomena do you begin with? Which phenomena are simpler and which are more complicated? You want to get to the simple ones because the complicated ones are complicated. Now, we all know both what the correct answer to this is and the answer that Galileo gave to explain this feather business, and that's that you're not accounting for air resistance, right? The reason they're falling not together is because of air resistance. Okay, you can say that, but we can prove it. I can prove it to you now. I have with me over there, and I will set this up, you will see. We have a tube, the coin, the feather. And what we're going to do is evacuate it to a pretty high degree. So we're going to close it up, and I have a vacuum pump over there. People at home are not going to have to sit and wait for this. It takes a few minutes. We're going to suck pretty much most of the air out of this thing.
Okay.
And see what happens.
Okay. We've got our vacuum ready.
Yes, we have now sucked a fair amount of the air out of this tube, and you can take it and now see how they fall.
All right, I've got it. All right, so we've got our feather and our coin here. And then if I just turn it, they fall at exactly the same rate now.
How about that?
in some cases, the feather appears to be going quicker.
Beat the coin, yeah. So I mean, look, that's a surprising thing. And your immediate thought that heavier means faster fall isn't right. So let's just look at how Newton explains this. It's very easy. Newton can account for this, but he's going to account for it in a certain way, and general relativity is going to account for it in an entirely different way. So this is where we really want to be keeping track of things. So the fundamental, this is just going very quickly through the derivation from the point of view of Newton about why those two objects, in the absence of any force except gravity, of course there's a force here because it's gravity making them both fall, why, if gravity is the only force, they fall together. So the fundamental dynamical equation of Newton's mechanics is as we would write it. He never wrote it this way, but we would say the net force, total force, is equal to the inertial mass. This little m is the mass of our object. And I'm calling it the inertial mass because it's the mass that plays the role in this equation. So it's the inertial mass times the acceleration. In other words, inertial mass is a measure of how much an object resists being accelerated by a force. The more the inertial mass, the less it will be accelerated by the same force. Now, what forces do we have? Well, here we've got the force of gravity, and we have Newton's equation for the force of gravity. So it says between any two bodies, little mg and big mg, and the g on mg is that this is the gravitational mass. That's different, conceptually different than the inertial mass. The inertial mass is just resistance to acceleration. The gravitational mass has to do with gravitational force. So Newton's equation is that the force of gravity between two bodies is a constant, Newton's constant, g. The mass of the little body, the mass of the big body, divided by r squared. It's a 1 over r squared force. It drops off with the square of the distance between the two bodies. This r is the distance between the two bodies. And the little e says the direction is, it's always an attractive force, and it's in the direction from one body to the other. So you've got the fundamental dynamics and the universal force of gravity. Now, let's suppose, it's not always true, it's not true when there's air resistance, that the total force, the net force, is just the gravitational force. Suppose we get rid of all the other forces except gravity, and suppose that the inertial mass equals the gravitational mass. Then we can just substitute here that the little mg is inertial mass times a, right, which is what we have up here, because we said little mg, the gravitational mass, the inertial mass are the same, at least proportional. That's equal to F net by this equation. That's equal to the force of gravity, because we said gravity is the only force acting. Then we plug in the force of gravity over here. And so we get this system of equations, and you'll notice over here, way on the left, there's little mg. And over here, way on the right, there's little mg. So those cancel out. And what we're left with is a claim that there is a uniform accelerative rate of gravitational freefall for any object, say on Earth, that's given by Newton's constant times the mass of the Earth divided by the square of the distance from the center of the Earth toward the center of the Earth. And because the little mg, the mass of the falling object, cancels, it's going to be the same acceleration for the feather and for the coin and for the moon. We talked about that last time. Newton says if I pulled the moon down and dropped it, it would drop at the same rate. This is Newton's explanation of that phenomenon. I mentioned before that this gravitational thing, you can say, oh, as Weinberg says, oh, well, this is instantaneous, blah, blah, blah. Look at the form of this gravitational force. It looks just like the electric force in Coulomb's law, exactly the same, except where here we have masses, here we have charges. It's a 1 over r squared. We have a minus sign because they're repulsive. But same thing. So that wasn't the problem. Anybody could have dealt with that. They did. They tried. Didn't work. Okay, so that's Newton's explanation for this experiment. Now let's just depict that in a space-time diagram. for Newton. So in this space-time diagram, we've got a big object that represents the Earth. We've got Galileo standing on top of his tower. He's going to drop two balls, a small one, a large one, and their two world lines track each other. They stay together. That's them falling together. Time is going up on this diagram. What are the forces involved here according to Newton? Well, Newton would say there's a downward force on the big ball, there's a downward force on the little ball or on the feather, whatever. There's a downward force on Galileo, for that matter. Mm-hmm. Because Galileo continues to stand on the tower, there is an opposing upward force on Galileo that's being produced by the tower. That's why he doesn't fall, right? You knock the tower out, he will fall. His natural, that's what he would do. So these forces balance out. The force of the tower and the force of gravity on Galileo balance out, so he doesn't accelerate, according to Newton. But once he lets go of the two balls, then there's an unbalanced force on them, the force of gravity. They fall together because of this equation. They accelerate the same, so they stay side by side, right? That's the Newtonian explanation of gravity. It's a force. It does what all forces do. Namely, it deflects things. Notice, again, for Newton, this is an unaccelerated path of the top of Galileo's head, and the balls are being accelerated as they fall, and their trajectories on this diagram are curved, indicating that acceleration. Now, what we're going to do is we're going to say we're going to completely change this explanation in general relativity, conceptually change it. And we're going to say, at the end of the day, these balls, when they fall, are not being accelerated. Their trajectories through space-time are straight, right? The indication of an unaccelerated trajectory is it's a straight line through space-time, what we call the affine structure. Well, how are you going to get that to work out? By changing the geometry of space-time. That's the key concept. We, as they say, geometrize away the force of gravity. Now, of course, we still have what we think of as gravitational effects. The apple still falls, the moon still orbits, the moon and the sun still orbit. All that stuff has to happen. And it happens pretty close to the way Newton says it does, although there are some corrections. But we're not interested in the little fiddly corrections. I mean, they were important for confirming the theory, the advance of the perihelion of Mercury and so on. We're interested in the concepts here. The concept is to say, look, in special relativity, space-time is Minkowski space-time. It's flat. It's like Euclidean space is flat. In general relativity, we're going to replace that with a curved space-time. And we're going to let the curvature do the conceptual work. Now, what we need to do is understand, what do you mean a curved space? I mean, people often get confused about this. They say, wait, how could a two-dimensional space or a three-dimensional space be curved unless there's a bigger space it's part of? And it's, in what direction, what's it curving into? If not, don't there have to be more dimensions? No. This is just the intrinsic geometry of this space. And we're going to go back, as we did with Euclidean geometry, forget about space-time, we're just going to talk about curvature for a minute. Okay, so this piece of paper intrinsically is flat like a Euclidean plane. What if I roll it up like that? It's still flat. Intrinsically, it's still flat. A straight line that I draw on this is still a straight line. So there's what's called extrinsic curvature, which is not internal to the thing, but it's how it's embedded in a larger space. Right. But then there's intrinsic curvature. That's not being embedded in anything else. That's in the space itself is curved. So here we have three different kinds of curvature just for a two-dimensional plane. Zero curvature, that's like Euclidean space, only here they've rolled it up into a cylinder.
Right.
Here we have our, where'd it go? Surface of a sphere.
A globe, an
A
inflatable
globe, yes. In this case, a globe, but a sphere. Think of it not as the edge of a three-dimensional object. Just think of it intrinsically as a two-dimensional object. A little two-dimensional flatland creature can live on this thing. This space is intrinsically curved. It has what's called positive curvature. We'll talk about that in a minute. And then you have these kind of hyperbole, like they look like the cooling towers of nuclear power plants. The surface of that is also curved, but it's curved, it has negative curvature. The positive and negative, I mean, there's a reason, but of course, it's just curved, okay? It's curved in a slightly different way. The plus and minus don't mean anything deep there. Zero curvature, positive curvature, negative curvature. So we need to just understand, well, what do you mean? How do you tell a space is curved? What geometrical effects, what geometrical indicators are there of the curvature of space? Now, there's a concept here, and again, I'm going to do this just quick and dirty, but you can understand it. An easy way to tell that a space is curved intrinsically is if you have the idea that you have an arrow that points in a certain direction, and you can transport it or move it along a continuous curve, but don't let it twist as it moves, right? Your path can twist, your path can do whatever you like. But as you move it, make sure it doesn't move. That's called parallel transport. Now, in Euclidean space, on the top of this diagram, we have the green point, the red point, and three different paths connecting, continuous paths from green to red. They're obviously different lengths, different curvatures. If we take this arrow, this vector, and parallel transport it, and notice nearby the arrows are always parallel, along any of these curves, we end up with the same thing. It doesn't matter. You can take any path you want. And so if I go around any loop here, suppose I take this arrow, parallel transport it to the red along that loop, and then parallel transport it back along the red path, it ends up where it started. It ends up with exactly the way it began. Okay? That's characteristic of a space of zero curvature. That parallel transport along a closed loop does not change the direction of the thing you transported. What happens on the surface of a sphere in a curved space? Well, we're going to play the same game here. And again, imagine you're a kind of flatland creature and you're here on the equator. You're somewhere on the equator. And someone hands you a stick that's pointing along the equator. And they say, now follow this path. You're going to, first of all, march along the equator a quarter of the way around the globe. But don't let the stick wiggle, right? Keep it straight, parallel transport it. Well, it's pointing along the equator. It'll keep pointing along the equator because the equator, the great circles here count as straight lines. They're the shortest paths in this space. So if I start here with this vector and I carry it along the equator, not letting it jiggle, not letting it move, when I get here, it's going to be pointing that way, still along the equator. Now, when you get there, take a right turn, this is a right angle, and start marching due north along a latitude line. Well, obviously, if I don't twist the arrow when I turn, then the arrow will now point perpendicular to that latitude line. And I will carry it a quarter of the way up all the way to the North Pole, and it'll be sticking that way, being parallel transported. Notice now it's pointing exactly the opposite direction of this last leg that I'm going to go down. So now I'm going to go from the North Pole back down to the equator where I began. I don't let this thing twist here at all. I just parallel transport it back down. Lo and behold, when I get back, it's twisted through 90 degrees. Okay? That tells me I'm not in a flat space.
I like this test. It's very nice.
It is. And this thing, I mean, in fact, you can characterize the curvature. This change in this angle is called the angular defect. And if you divide the angular defect by the area enclosed, you get the average curvature. So these are things you can check, right? As long as you can carry things and be sure they're not twisting, you can get your hands on whether you're in a curved space or in a flat space. And in a negatively curved space, it'll twist one way. In a positively curved space, it'll twist the other way. Now, the other things you notice here that people will often point out, this little triangle that this three-legged journey that you did in this diagram on the sphere, that's a triangle, because this is a great circle, that's a straight line, this is a great circle, that's a straight line, this is a great circle, that's a straight line. So this is a triangle in spherical geometry. It's a rectangular triangle. Why? It's only made of right angles. Right angle here, right angle here, right angle here.
Huh.
That's what a rectangle is, right? Doesn't have to have four, it just has to have all right angles. It's literally a rectangular triangle.
That's very funny.
Right? The interior angles obviously add to more than 180 degrees. That's an indication you're in positive curvature. If they add to less, as in the little triangle that's drawn here on our negative curvature, you'll notice these angles are getting narrower and narrower, so the interior angles are adding up to less. So if you have the notion of parallel transport, then you have your hands on a way to test for curvature. Now, this thing is a very poorly done diagram by me. I couldn't find a good way to do one. I just wanted to illustrate something that you kind of often don't see, which is that here, what this is supposed to be is a two-dimensional plane that's flat out here. It becomes like Euclidean. There's a lump in the middle. So what does that mean? It means here on the top of the lump, there's positive curvature. Here where the lump flattens out again, there's negative curvature, because that's sort of like a saddle point. And out here, there's zero curvature. So this is a space of zero curvature. If I parallel transport all the way staying out here in the flat part, of course, I'll get no curves. That tells me the net curvature in here is zero. The positive is balancing the negative.
Right.
So now you can, you start when you do this to talk about curvature, and you start with spaces of constant curvature. The surface of our globe is positively curved. Furthermore, the curvature is constant. And on our hyperbolic thing, it's supposed to be like that too. It's negatively curved but constant. But you can also then have spaces of variable curvature. The curvature is different in different spots. To handle that, you need to learn differential geometry. So there was a bunch of mathematics of how do I do geometry where the geometry of the space can be changing from place to place. I do it in little patches. I deal with each little patch. And so you have to learn all the techniques of differential geometry. This Einstein had no idea about. A lot of this mathematics was developed exactly to deal with general relativity and so on. So what we're going to do is we're going to take our flat Minkowski. Oh, before we do that, notice, and I guess everybody knows this, but just to remind you, when we try to make Euclidean pictures of non-Euclidean spaces, things can't go perfectly well.
Right. Maps of the world are very distorted.
Maps of the world are very distorted. The Mercator projection, distorts so that small objects toward the North and South Pole look very big on the projection. This is a projection. You might say, but why do you use the Mercator projection? Because it messes up the areas so much. This is actually an explanation of why. I just wanted to explain, because there are other projections. There are like a million different projections.
Yeah, so what are the two images?
These are the same images. This is the North. Oh, sorry. This is North America. That's Spain, right? You're talking about sailing from, I can't remember, Cuba. I think Cuba to Spain, okay? And you might think, okay, what you would like to do is go along the shortest path. The shortest path is a geodesic. It's straight. If you just took on your globe a piece of string between 2 points and pull it as tight as it'll go, so you get the shortest path. In Euclidean, in a Riemannian geometry, the generalization of Euclidean geometry, that's the shortest path. You might think if you're sailing in a boat, I want to do that. I want to go on the shortest path. But you don't. Why not? Because if you're sailing in a boat, you got to steer. And one of your instruments you can use to steer is a magnetic compass. And absolutely the easiest way to steer is if you're always on the same magnetic heading. So you just look at your compass, you say, we're going to go south-southeast to this compass point. And as you are steering your boat, you just look at the compass and you always keep that needle. Okay, that's called a rhumb line, a line where the magnetic direction doesn't change. In a Mercator projection, this blue line, see that straight one on the map? That's a rhumb line. It's not the shortest line. This red line would be shorter. This would be a shorter path for our boat. This one's longer, but if you're a captain, you're saying, I want that one. Why? Because I can just pull my Mercator projection, throw a straight edge on it from where I am to where I want to go, take a compass heading and say, follow that compass heading. So, I mean, again, there are lots of different projections. The Mercator projection, of course, messes up areas. There are ones that keep the areas right and squish other things. You always give something up, right? Because you can't take a curved surface and put it on a flat one. It doesn't work. Okay, so what does that mean? We're going to now have space-time diagrams of curved spacetimes. And you have to be a little careful about interpreting them because the diagrams are Euclidean. The diagrams are flat Euclidean. They're diagrams of curved things. So you have to be careful. In Minkowski spacetime, because Minkowski spacetime is flat, the Minkowski diagrams, very easy to read off. A straight line is an inertial trajectory. Okay, yeah, I mean, you have to be worried about distances. They don't work the way you think, but some things are really straightforward. In general relativity, nothing's straightforward. All of these diagrams are compromises, and they all involve adopting certain conventions. But let's understand how those conventions help. All right, so here's the fundamental gravitational issue that Newton was dealing with, as we know, which was the solar system. So Newton, at the time of Newton, we had Kepler's laws. Kepler would say, oh, these orbits that we thought were circular, they're not circular, they're not uniform circular motion, they're actually ellipses with the sun at one focus. There's the equal area law, we don't, but all this stuff was known. Newton is trying to come up with a theory of gravity that will give him all of these phenomena. And this is the way we usually depict the solar system, that there are these orbits, right? And the orbits, again, these are ellipses and the sun is at one focus and they go at different rates around. I've been involved, actually I'm going back again, in the Science for Monks and Nuns program that the Dalai Lama set up, teaching science to Buddhist monks. And the last time I was there, I was teaching to the adult monks, but there are also these schools for the kids. And they said, can I go to like the high school and just answer whatever question comes up? Science question. Sure, fine. So I go, and the very first kid to ask a question, he came up to draw on the board. He said, I don't understand something. Can you explain something to me? And he drew the solar system just like this. So here we've got in this diagram, and this is off of, I think, a NASA website maybe. Sun, Mercury, Venus, Earth, Mars, asteroid belt, right? Jupiter, Saturn, Uranus, Neptune. Some comet doing some funny thing. So he kind of draws this and he says, why are the planets always lined up like that? And, it stops you for a minute because more than 9 times out of 10, it's drawn like that and they're in a straight line, which essentially never happens, right? At any random time, Jupiter's here and the Earth is way over here and Mars is here. They're just scattered. But we always draw them punk, 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 maybe so you can look at their sizes or something. But my point, and this is a point about be careful about diagrams. This kid perfectly reasonably thought they're drawing those diagrams because they're always lined up. And I had to explain to him, no, they're just confusing you.
No, that's a very good story.
It was fun, right? I mean, this is the same thing I'm saying. We project coordinate systems. We project, there's all kinds of tricks in reading these diagrams that often we get so used to that we just use them without thinking about it.
My favorite example of this is the false light images of the Hubble telescope. Naturally, those aren't diagrams per se, but most people think that that's what some nebula actually looks like from the naked eye. But in fact, you're seeing images of X-rays, gamma rays, whatever, that have been shifted in the spectrum to the visible light spectrum.
So, you know, there's the nice thing for somebody who's visual like me. I like pictures, right? They help me understand. But, you know, there's a danger. You have to think hard about the pictorial conventions, or you're going to get confused. So Newton's going to think, we know how Newton's going to think about this. He's going to think about it this way, right? He's going to say, okay, this is as it were at a moment of time, but here's the sun at the center of the solar system, and then here are these two different planets, I don't know, Earth and Mars, one orbiting faster than the other. The reason this faster orbit means it's more accelerated. It's more accelerated because it's closer to the sun. The gravitational force is higher. That's the way Newton would understand this, right? If we turn it into a space-time diagram. The basic idea of general relativity is very simple. In the intrinsic geometry of space-time, this and this are straight. They're not accelerated. There's no force. These trajectories through space-time are straight. The fact that it orbits, unlike what Newton said, I need a force for it to orbit, general relativity says, no, you don't. You just need to change the space-time geometry. And as soon as you see that, you see, oh, then of course a light object and a heavy object will, as it were, their trajectories will go side by side because their weight has nothing to do with anything. The mass has nothing to do with anything. They're just on inertial trajectories. They're just on straight trajectories. And nearby straight trajectories are nearby in space-time. That's the fundamental idea of general relativity. Now, you have to be careful. People say a lot of very confused things here. One thing they say is, oh, in general relativity, you curve space, and then these orbits become straight. No, not at all. These are not straight, right? They're not spatially straight, right, at all. If I take an object and throw it, you say it goes down on some, that line is not straight in any spatial geometry. It's in the space-time geometry that it's straight. It's the space-time trajectories that are straight. And then they'll put the Earth and then like it's on a trampoline and it pulls it down and, you know, blah, blah, blah. All that stuff is like, not really. The main thing is to think in terms of space-time and to think in terms of the space-time trajectories. And the basic idea is that in the absence of any force, something will follow a straight trajectory through space-time, and gravity isn't a force. And the reason you get orbits is not because there are forces, it's because of curvature of space-time. And now we've got the general relativistic explanation of it. We've still got the Earth, we've got the tower, we've got Galileo. We've got the force of the tower on Galileo. That's there, he can feel that on the bottom of his feet. That's a force up. Right? The tower is pushing him up. There is no counterforce of gravity, right? When we did with Newton, Galileo was unaccelerated because the force of gravity down was counterbalanced by the force of the tower up. But now we have the force of the tower up with nothing counterbalancing it. Galileo, this trajectory is now curved in space-time. The balls, those are straight. They fall together because nearby geodesics run pretty parallel to each other. Okay? Mm-hmm. Now, if you just keep that in mind, the balls are falling along straight trajectories. Galileo, standing on the tower, his is curved. This is curved. This is accelerated that way. In fact, it's a constant acceleration. It should remind you of our Rindler observers. Remember our Rindler observers following these hyperbolae, they were constantly accelerated. That's this guy. Okay? Now, it's often said, because Einstein said it and people repeat it, is that the way he finally got to this theory, he's struggling, trying to get a theory of gravity. And finally it strikes him, he says, it was the happiest thought in his life, what people call the principle of equivalence. And the way he says it is he suddenly realized that if you were on an elevator on Earth and a cable snapped, so you were in free fall, which means, again, from a Newtonian perspective, the only force on you is gravity, that until you hit the bottom, you'd feel like you were just in interstellar space floating with no gravity, right? Mm-hmm. He said, this is what got him there. Now, let's be very careful here. This is the source of a million misunderstandings. So this thing is called the equivalence principle. People will talk about the equivalence principle. I got this off the web too, Blanche Booker, thank you. I changed it, I cheated. She had equal signs here. I put these approximately equal signs because the correct statement, this is the correct statement. When people would equal signs, it's the wrong statement, then you're gonna get really confused.
Okay.
The equivalence is the near equivalence of, there are two of them, okay, two pairs of this is equivalent to that, this is equivalent to that. One of the things that are almost equivalent is a box stationary in a gravity field. So you've got just somebody like us sitting on the surface of the Earth. We would say we are in a gravity field due to the gravity of the Earth. We are stationary because we would say we're not moving. We feel this pull down when we drop things. Now we have somebody who's in empty space, no gravity, zero gravity. There's a rocket that's accelerating them at a constant rate, the same g acceleration. This box is tied to a rocket pulling it upward. This is almost equivalent to that. And then the other one with the box falling freely, this is like you're on Earth, you're in the elevator, but the cable broke, so now you're in free fall. Or you're out here in empty space, just floating around. Those are almost equivalent.
The question is why, but you're about to tell me that, I'm sure.
Why the almost? Or, okay.
Well, both.
Yeah. So the almost is more important here. I just want to get this clear, because if you don't, I'm going to show you in a minute, if you put that equals here, you're going to get terminally confused. So there are really two principles of equivalence. One is the one that just has to do with gravity affecting massive objects. And sort of Newton could say that. That's called the weak equivalence principle. And that's basically following the little Newtonian argument we gave that because the force of gravity scales with the inertial mass, that drops out of the effect. Now, if you take the weak equivalence principle and you say, yeah, but does gravity have any effect on light, for example? Right? Light is not a massive particle. Newton would presumably say, no, why would it? The force of gravity is gm1 m2 over r squared. If one of the m's is 0, no force of gravity, it'll have no influence. The strong equivalence principle, and this is part of what Einstein realized, is just to say, let's assume that every phenomenon, optical, anything, in these two cases will be nearly alike. That immediately gives you the so-called bending of light by gravity, because it's clear that light, if a light ray were going across this box, because it's being accelerated upward, it would hit the far end lower than it hit the incoming part, right? The light ray is just going, as it were, across. But because the box is being accelerated upward, it'll hit here lower than it comes in here. So from this person's point of view, they're going to say, oh, the light bent, right? So the strong equivalence principle takes you out of just being restricted to massive objects, which is the only things that Newton would say are affected by gravity at all, to everything. Why is this not equals? All right, let me just show you that very easily. Suppose you're this person. So we're very much like back with Galileo's boats, right? You're in a boat. Can you do something inside the boat that'll tell you whether the boat is anchored or sailing, right? Can you do an experiment? Now, suppose you're here and you've got all kinds of measuring instruments. You can't look out. You're confined within your box.
By here, just for our listeners.
I'm sorry. You're in a box accelerating with a constant acceleration in empty space in a certain direction, which we'll call up. Okay? Constant accelerated up, the box is being pulled up. Things, as it were, seem to fall because when you let go of them, they don't keep up with the box anymore because, they're not attached to the rocket anymore. Okay, so here's an experiment you can do. You do it really carefully, very precisely. You take two objects, you put them exactly 1 meter apart up here, and at the same moment you let go of them, and you mark, it actually doesn't matter, it's the same moment anyway. You let go of them and you mark where they hit the ground. How far apart will they be? How far apart will those marks be in this case? Same space. If it's 1 meter here, they'll hit the ground 1 meter apart. Suppose you're in a box in a stationary gravitational field on the surface of the Earth. And you take two objects, you take them 1 meter apart here, and you let go of them. And you carefully measure where they hit the ground. The force of gravity, just think in Newtonian terms, the force of gravity is toward the center of the Earth. Those are going along radii toward the center of the Earth, which are getting closer and closer. So these objects will hit a little bit closer together than you let go of them. And so you could tell. That's why I put approximately here. It's a very small effect in that case. You'd have to be very precise about it. But you could tell whether you were in this situation or this situation. And similarly in this situation. Freely falling objects do not behave, okay, like boxes that are just in empty space, interstellar space with no, as we would say, no gravity. That is essentially in Minkowski spacetime. Those deviations are called tidal effects. One obvious way, if you're in the space station, the International Space Station in orbit, you're in free fall. That is, the only force is gravity. Could you tell that you're in orbit and not somewhere in interstellar space? Here's an easy way. Take a drop of water. You know you're weightless. You just make a little drop of water. If you're in empty space, that'll be a perfect sphere. If you're in orbit in the space station, it will be slightly elongated in the axis toward the Earth and squished in this way. Now, you know this because everybody talks about falling into a black hole and getting spaghettified, and you've talked to people who've talked about falling into a black hole and getting spaghettified, right? Mm-hmm. Spaghettification is a very strong instance of this tidal effect that tends to pull things apart this way and squish them in this way. But those objects are in free fall, right? So if you believed that free fall was just like moving through empty space, you'd say, but if I'm moving through empty space, I don't get spaghettified. What are you talking about? So that's wrong. It's almost right. It's kind of, you say, oh, but if I approximate, I have to go small. I go, the effect gets smaller. Yeah, but still it's there. And if you fall into, if you're in a black hole situation, it gets quite dramatic, as a matter of fact. You had a whole discussion. How do I survive it? There's no discussion. How do I survive moving at space through a constant velocity? So free fall better not be always the same, and it isn't. Okay. But the idea, so it's the equivalence principle, the important thing is not that there's an exact equivalence there. The other mistake that people make, and we're going to see this in spades, is that the equivalence principle says, oh, any gravitational effect can be mimicked by an acceleration, or any acceleration can be mimicked by a gravitational effect. That's 100% false. That's nonsense. And oh, it's the equivalence principle. No, it isn't. Okay, so here's the general relativistic explanation of Galileo's experiment. These are straight lines. That's a curved line. You have to understand the space-time geometry. We did, remember before, we had the rotating spheres for Newton and the rotating spheres in special relativity, and then we replaced them with clocks, because the clocks then were measuring the proper time. So here we're now going to drop a clock. We know the trajectory, but now we have to think about, in general relativity, what's the length of this trajectory? How much time is going to run off on this clock? How much time is going to run off on Galileo's clock? How much time is going to run off on a clock that's sitting at the bottom of the tower, that's also constantly accelerated, right? Because it's being pushed up by the ground.
Right.
Well, we already know. We know that in general relativity, in general, including special relativity, the longest curves, the ones that show the most time, are the straight ones. And we know that the green one, the free fall, is the straight one. So this clock is going to run off more time than an equivalent clock being held by Galileo up on top of the tower. And that's going to run off more time than a clock sitting at the bottom of the tower. Why? The one at the bottom of the tower is even more accelerated. Galileo up here and this one are like our two Rindler observers, the one more and less accelerated. The more accelerated one, the more their clock, as it were, slowed down, if you will. That's all that's going on here. That very same effect we saw in special relativity of the Rindler observers is this so-called gravitational time dilation effect. And this can be checked because you have hyper precise atomic clocks. And literally, you can take two atomic clocks, synchronize them, lift this one up this far, a foot, sit it on the table for a while, put them back together, they're not in sync anymore. And the one you lifted up will show more elapsed time. Why? It was less accelerated. Because as I lifted it up, the trajectory became closer to being straight. So that's, the effect of the space-time geometry on clocks is just given by the curvature of the geometry. So this thing at the top is called the Einstein field equation. It's what he writes down in 1915 after this breakneck race with David Hilbert. On this side, on the left side, is a thing called the Einstein tensor. This R mu nu is a curvature tensor, the curvature scalar, the metric. Okay, I can give these things names. But you have this equation that this all has to do with the geometry of space-time. And on the other side, K, T mu nu, this is called the stress energy tensor. That T mu nu, that's supposed to kind of represent the distribution of energy, if you will, matter and energy in space-time. So the fundamental equation that Einstein has is connecting distribution of matter and energy in space-time to space-time curvature. So that gives you the idea, lots of matter and energy in the sun, it's going to have a rather large effect on space-time geometry. That's why these planetary orbits that on our diagrams don't look straight at all, they are. And sitting in this K is Newton's constant, G. So you can sort of see why Newton's equations could approximately arise. I don't say you can see how they do, but that they could approximately arise. I mean, you've actually stuck Newton's constant in there. Now, 2 points about this equation. This is a quote. I finally dug it up. And this is the exact quote in German. I won't read, my German's not that good, but if anybody's interested, you can freeze that and read the German. But the English translation He's talking about this equation, his own field equation. He says, it's similar to a building, one wing of which is made of fine marble, left part of the equation. The other wing is built of low-grade wood, right side of the equation, the T mu nu part. What did he mean by that? Because that's a very deep, again, Einstein right on top of his game, understanding what he's done. He says, look, these are pure geometrical concepts on this side. They're sharp. Understand differential geometry, you understand the geometry of pseudo-Riemannian spaces, variable curvature, these are sharp. This T mu nu, that's a crummy approximation. That can't really represent in full detail the energy density or the matter or anything like that. It's just a rough approximate, sketchy thing. Why? Again, he didn't have a better theory. 1915. You don't even have quantum, new quantum mechanics. He didn't have anything better to work with. He stuck in a thing that made this a mathematically reasonable equation, because the two sides have to match mathematically. But he knew from the beginning that stress energy tension, that's crap. It's okay, it's some good approximation. It can't be absolutely right. He knew that had to be improved. Just as we saw at the beginning when he said, at the end of the day, I have to give you an account of how clocks work. At the end of the day, I have to give you an account of rods, if I'm going to talk about them. I'm doing something a little shifty here, okay? And I have some promissory notes, okay? That's really important. It's very important to understand that from the beginning, Einstein never thought this field equation was precise, physically. Mathematically precise, not physically, because T mu nu, that's not a real physical thing, some approximate thing. Second point about this equation. John Wheeler famously said, and people repeat this a lot, you understand why he said it. He says, space-time tells matter how to move, matter tells space-time how to curve. That's how he summarizes this equation. Space-time tells matter how to move. That's because in free fall, things move along geodesics. They move along these straight trajectories through space-time. Matter tells space-time how to curve. That sounds like this equation saying, well, here's the matter telling the space-time how to curve. That's not quite right. And the reason it's not quite right is that this side is not the space-time curvature. It's something derived from it, the Einstein tensor. But there are lots of different vacuum solutions of Einstein's field equations. A vacuum solution is one where this T mu nu is everywhere zero. So intuitively, no matter at all. You'd think, well, if matter tells space-time how to curve, if there's no matter, it must be flat. Lots of different vacuum solutions. Not flat. Not flat at all. With no matter around. Matter influences how the space-time curves, but it doesn't determine it. And in fact, this might surprise you. The first black hole solution, vacuum, no matter, anywhere. T mu nu, zero, everywhere. So when people say, oh, sitting at the middle of a black hole, there's all this matter that got crushed down to a point. There ain't no matter anywhere in the Schwarzschild solution. So this is just so I said I gave you the example of Feynman getting the twins paradox wrong. This is one he got absolutely right, and this is fun. So this is from Surely You're Joking, Mr. Feynman, and it tells you about Feynman, sort of why some people liked him. Okay, so I'll just read it. He says, I often like to play tricks on people when I was at MIT. One time in a mechanical drawing class, some joker picked up a French curve, a piece of plastic for drawing smooth curves, a curly, funny-looking thing. It turns out they're different French curves. They have these, they are strange, curved, smooth curves with different amounts of curvature. And I said, I wonder if the curves on this thing have some special formula. He said, I thought for a moment and said, sure they do. The curves are very special curves. Let me show you. And I picked up my French curve and began to turn it slowly. The French curve is made so that the lowest point on each curve, no matter how you turn it, is tangent to the horizontal. The tangent is horizontal, right? The tangent to the curve is straight across, right? All the guys in the class were holding their French curve up at different angles, holding their pencil up to it at the lowest point, and laying it along and discovering that, sure enough, the tangent is horizontal. They were all excited by this discovery, even though they'd already gone through a certain amount of calculus and they'd already, quote, learned that the derivative, the tangent, at the minimum lowest point of any curve is 0, horizontal. They didn't put 2 and 2 together. They didn't even know what they knew, right? It's obvious at a circle, right? The lowest point, the tangent is horizontal. I mean, any curve, as he says, any curve. And then he makes this very nice comment to me. I don't know what's the matter with people. They don't learn by understanding. They learn by some other way, by rote or something. Their knowledge is so fragile. So he starts with this saying, look, if you really understood, you'd understand what I was saying was a joke, right? There's nothing special about French curves that they have that property, because all curves have that property. Now he gives the example we care about. I did the same kind of trick 4 years later at Princeton when I was talking with an experienced character, an assistant of Einstein. I think we can guess who that was, but I won't hazard the guess, who was surely working with gravity all the time. I gave him a problem. You blast off in a rocket, which has a clock on board, and there's a clock on the ground. 2 clocks, stopwatches. You get one. You're in the rocket.
Okay.
Okay? I'll stay on the ground. The idea is that you in the rocket have to be back when the clock on the ground says 1 hour has passed. Now, 1 hour is too long to wait, but suppose I said, I'm going to set this for a minute, right? When this one that I'm holding in my hand is at a minute, you have to be back here so we can compare side by side. Remember, to really compare clocks, we have to have them side by side. We can't compare distant clocks because that depends on some arbitrary definition of simultaneity, which is only coordinate dependent. It's not physical. So to really compare clocks, like in the twins case, we start with them side by side, we end with them side by side, and we see who's run off the most time. Okay. Now, what you want is that when you come back, your clock is as far ahead as possible from mine, right? You want to run off more time on your clock. Now, according to Einstein, if you go very high, your clock will go faster. We just saw that with Galileo at the top of the tower. His clock is ticking faster than the one at the bottom of the tower, right? Get it out, as it were, upward in the gravitational field. According to Einstein, if you go very high, your clock will go faster because the higher something is in a gravitational field, the faster its clock goes. But if you try to go too high, since you've only got an hour, you have to go so fast that to get there that the speed slows your clock down. That's the twins effect, right? If you get in your rocket and go really fast up and come back down, now we're kind of back to the twins, and we know that twin actually less time. So you'd like to get your clock really high up quick, but not too quick, maybe not too high. I mean, the higher the better, but the higher the quicker, right? So you can't go too high. The question is exactly what program of speed and height should you make so you get the maximum time on your clock? So you understand the problem now, right? We're going to go. We're both going to hit this. In 1 minute, when mine says 1 minute, you've got to be back here. You can do anything you want. You've got to be back here with your clock to compare to this one. You want to run off as much time as possible. I have 2 events. I have all these different trajectories, right? These different continuous trajectories from one to the other, these paths. Mm-hmm. We know that in Euclidean geometry, what the shortest path is, right? Straight line. Mm-hmm. We want the longest path. We're running off time, but we're not in Euclidean geometry anymore. We're in relativity. You already know what the longest path is. The one that runs off the most time. It's the straight one, right? Mm-hmm. Now, the straight one is the one in free fall. the one that's, as it were, only affected by gravity, as soon as I click mine, you throw yours up so that it's just in free fall at the right speed, so that exactly at 1 minute, when this one hits a minute, yours comes back. It's always just in free fall. That, according to general relativity, is the straight trajectory. And we know the straight trajectory is the longest one. Right? So what you need to do is just think how hard, I mean, you'd have to calculate this, but the basic question is, how much of a shove should I get it? And then I don't touch it afterwards, right? You're in a rocket, you could be doing all kinds of things with it, right? You could be flying around this way and that way and everything. No. So let's see what Feynman says. This assistant of Einstein worked for quite a bit before he realized the answer is the real motion of matter. By real, he means the geodesic motion, the free fall motion. If you shoot something up in a normal way so that the time it takes the shell to go up and come down is an hour, that's the correct motion. And you can see that from just what we've said today. Because according to general relativity, the free fall motion is straight through space-time, and the straight trajectory is long. At least it's the longest. Any small deviation will make it shorter. And clocks are measuring that length. So if you want to run off the most time on the clock, have the thing be in free fall. Right? Don't put a rocket on it. Don't accelerate it in that sense. It's the fundamental principle of Einstein's gravity. That is, what's called the proper time is at a maximum for the actual curve. The actual one meaning just let it go. But when I put it to him about a rocket with a clock, he didn't recognize it. He was just like the guys in mechanical drawing class, but this time it wasn't dumb freshmen. So this kind of fragility is, in fact, fairly common even with more learned people. I think this is very, I mean, this is the same point Bell was making with his example. He's in the theoretical division of CERN, asking questions about special relativity, and they're getting them wrong. Einstein's asking an expert on general relativity a conceptually simple question, and he's getting it wrong. Mm-hmm. He can calculate. They could calculate. Yeah, they can grind the numbers out. He would put them in the right equations, and he would get to the right answer. But he doesn't understand. There's a couple more things, and I'm going to try and go these pretty quickly. One is, I'm sure you've talked to people who've talked about the cosmological constant, right? That comes up a lot. Mm-hmm. People doing cosmology. So what's the story with that? We had the original equation that Einstein wrote down was just this, that this Einstein tensor was equal to k T mu nu. And what he realized after a while was that would not give him a static universe, that no matter what he did, a universe governed by this equation would always either be expanding or contracting. And he wanted an infinite, eternal static universe. So then he stuck this extra term in. It's very constrained about the mathematical form of this. And this works, and this lambda is just a constant. It's called the cosmological constant. So Einstein sticks in this thing, lambda, so that he can have a static solution. Well, 2 points about that. One is that, yeah, you can get a static solution out of this, but it is an unstable equilibrium. That is, it's like balancing a pin on its top, on its point. If you get it exactly right, it's stable, but if you tip it, it's static, but it's unstable. If you tip it even a little bit in any direction, it'll fall over. So he could not get a robustly static solution with this. So it didn't even fix his problem. But the other thing was then later Hubble finds that there's this expansion, that all the galaxies are moving away from each other. I'm sure you've had people talk about this in the redshifts. And so he didn't even want a static solution anyway. If he had a static solution, he wouldn't have these Hubble shifts. So what he does, he puts it in, and then he later says it was the biggest mistake in his life. If he had never put it in, he would have predicted Hubble. So he takes it out. Now you know people are putting it back in, right? Why? Because without it, you get this expansion, but it slows, but now they're finding the expansion is accelerating. Okay, and they say, well, one way to get the acceleration back is to put the cosmological constant back in. Now, I don't want to go into a lot of detail, but I want to make a very, again, important conceptual point here. This is the way Einstein did it. Okay, I have this lambda g mu nu right here. This is the way people, the cosmologists, do it. You'll notice it's a minus lambda g mu nu over on this side. Now you might say, who cares, right? It's just math, same equation. Who cares whether I put it on this side or on this side of the equal sign? But remember, Einstein said this side is fine marble, and this side is low-grade wood.
Mm-hmm.
This side represents energy and matter, right? So if I stick it over here, I say, oh, this is dark energy. And then you say, dark energy, what's that made of? And furthermore, it's negative. Notice that minus sign now. You say, wait, negative energy. There's some weird negative energy pervading the universe. What's that made of? Is it 0-point quantum energy, blah, blah, blah? I mean, you've talked to people. I'm sure they say things like this, right? What is the dark energy that makes up 25%, whatever? But if you stick it over on this side, no energy. It's just another term in this equation. Now, I heard an interview on the radio with Roger Penrose. He was talking to this guy on NPR. And the guy kept saying, but what is dark energy? And Penrose just kept saying, it's just a number. Just a number. What are you asking? And Penrose was thinking of it this way. It's a modification of the fundamental law, but the lambda is a constant. It's just a number that sits here. And the people who put it over here say, well, really, the fundamental equation is the same. I've just added a new stress energy term on this side. I have to understand where this comes from and whether it's constant. So all of that debate comes out differently depending on whether you write the equation this way and think about it this way, or write the equation this way and think about it this way. Good. So let's get to the main example everybody talks about what happens in general relativity, a black hole. A black hole is a solution to the Einstein field equations. The original one discovered by Schwarzschild is a vacuum solution. There is no matter anywhere. And it's an eternal black hole. It's always existed. It didn't come from anywhere. That's not a physical thing, right? Physical black holes come from collapses. But the way to understand a black hole is through a space-time diagram. This is a Penrose diagram of a black hole. This is another diagram of a black hole. Same thing, different pictorial conventions. Notice here, the light cones are always at 45 degrees everywhere. Here, the way in this convention, they're always at 45 going away from this central axis that we call the singularity. But as you approach it, the outside one tips in. It tips further and further over. So these light cones narrow down and become skinnier and skinnier. These light cones are these light cones. They're the same. These are just different representational conventions. The light cone structure here is the light cone structure here. So you can read off either of these what's going on. But if we look at this one, and I just want to make some points about this. Here is so if in this diagram, again, the outside part of the light cone keeps tipping, tipping, tipping. At a certain point, it reaches vertical. And at the point where it reaches vertical, you get this cylinder called the event horizon. And the characteristic of the event horizon is that if you're inside the event horizon, then even light will never get out of it again. Why? Because it's always tipping further in, right? So light is trapped in the event horizon, as it were, right? Mm-hmm. The exterior, suppose I'm an exterior observer here. I can stay outside of the event horizon. If I ever pass beyond it, I'm never getting back out again. To stay at a constant distance, as it were, from the event horizon, I have to accelerate. So I'm really a Rindler observer. I'm one of these people with a constant acceleration. My clocks are being affected by that and everything. Okay? Mm-hmm. If an explorer goes through the event horizon, okay, they just keep going. They're not going to notice anything here. There's no funny business that happens at the event horizon. There's nothing physical that could happen at the event horizon locally. People who say things like, oh, there's going to be a firewall, or there's going to be this or that, or, membrane, or whatever the heck. No, there can't be. Not according to general relativity. Why? The event horizon isn't even a local object in space-time. The event horizon is a globally defined object. So there's no way any physical effect can happen on this explorer who goes off of the mothership and passes the event horizon right there. There can't be a meter or an event or an observable thing or anything that happens there. If they just go, if they just let themselves go, they'll follow a trajectory, a straight trajectory that will end up here at the center in this diagram at the thing called the singularity. This trip, like our Zenonian observer, will be a finite proper time. They'll run out of time. The length of this path in proper time ends. I mean, it's finite. There's only so much of it. This observer who falls in past the event horizon, over on this diagram, what they're doing is this. That is, this singularity, this jagged thing in the Penrose diagram, is this singularity. The vertical thing in this diagram. This diagram is like what Bob Garrosh uses in his book. What is the significance? The problem is people look at this diagram and they say, oh, the singularity, there's an infinite amount of mass piled up here. No, there's no mass. It's this, it's an edge to space-time. And the reason you know that this cuts this way and not this way, as it were, is you notice as these light cones get thinner and thinner and thinner, the singularity cuts across the tops of them, right? It cuts across them this way, cuts across the top, like this. So the Penrose diagram tells you in a much clearer way what's going on in space-time than this does. The other thing about this that is helpful to all of our discussions that I've put on this, and really one of the last things I need to say here. Here I have twin A and twin B. They're out here outside the event horizon. Because of the gravitational effects, twin A can go that way around this and just be in free fall. And twin B can go this way around this and just be in free fall, and they can meet again later. So they can synchronize their clocks here, and they can meet again later and compare their clocks with nobody accelerating. They're in free fall the whole time. They're following geodesics the whole time. Their clocks can be different. They can have run off different amounts of time. Why? Those trajectories are different lengths. You have to calculate the length. Can't look at that diagram and tell. Depends, all kinds of ways you could do that. So this, again, general relativity puts the last nail in the coffin of the idea that the twins phenomenon has anything to do with acceleration, because you can produce the phenomenon in that theory with no acceleration of anybody. Okay? So that's done. Now, if you want to know what anybody sees, literally sees, what light gets into their eyes, you can read it off these diagrams because they have the light cones. Just follow the light, see what they can see. We already saw that in special relativity, our Rindler observers, there are certain things that will happen they'll never see because their trajectories will never intersect the future light cones. So if they're looking in certain directions, if somebody's doing something, they'll never see the end of that. Why? Not that it didn't end. Of course, it went on. The person did the stuff. The light just never gets to them. That's all. There's nothing deep in that. There's nothing extraordinary about it. But when people talk about these event horizons, they say, oh, in the exterior, the person sees the person falling through the event horizon going slower and slower and blah, blah, blah. Yeah, that's what they see. So what? It's not, they go right through the event horizon. And they would understand why they're seeing what they see if they understand general relativity. They could say, oh, there's a limit to what we'll see because there's a horizon here. This is just so people will know the original black hole solution was a vacuum solution. This is the full Penrose diagram of it. You'll see this sometimes. There's a future singularity and there's a past singularity. That is, there's kind of a white hole, but this is empty everywhere. There's no matter in this at all. So when people say, what happened to the matter? In this thing, there never was any, ever, anywhere. A real black hole, this is from the Hawking and Ellis book. A real black hole, of course, forms when a star collapses. So this is supposed to be a Penrose diagram of a real black hole, and this indicates the matter of the star. So this is the trajectory. The star grows, and as long as it's burning fuel, it can stay against the tendency to coalesce. When the fuel runs out, it crunches down, right? Tidal effects and all that stuff. And then you form an event horizon, you have a singularity here, and this is supposed to be the matter of the star. But it's not correct to say the matter is somehow hanging out at the middle, because the singularity is a singularity. It's an edge in the forward direction of time. It's where time runs out, right? All of these are a finite proper time. Steven Weinberg, in his book To Explain the World, page 251, says this, and I hope everybody who understands what I've said will see this makes no sense. I mean, there's just a technical mistake, but it's not even that, it's the conceptual one. So here's what Weinberg says. The success of Newton's treatment of the motions of the planets and comets shows that inertial frames in the neighborhood of the solar system are those in which the sun rather than the earth is at rest or moving at constant velocity. According to general relativity, this is because that is the frame of reference in which the matter of distant galaxies is not revolving around the solar system. Already, that's entirely false. We haven't brought in distant galaxies in any of this. General relativity doesn't care about distant galaxies. General relativity can give you a perfectly good account and would give you essentially the same account of just the solar system if there were no distant galaxies. And therefore, it was Mach's idea that somehow the distant galaxies must be accounting for all of this stuff. Newton rejected that. Special relativity rejects it. General relativity rejects it. It could be vacuum out there, and you can have basically the same solar system as we have. And it would still be the case that Copernicus was right and Ptolemy was wrong. Let's go further. In this sense, Newton's theory provided a solid basis for preferring the Copernican theory to that of Tycho. Now, Tycho, if you remember, Tycho took the Earth and put it at the center at rest, and then the sun going around it and the planets going around the sun. So a funny kind of system. But in general relativity, we can use any frame of reference we like, not just inertial frames. So let's just stop on that sentence. Yeah, we can do that in general relativity. We can do that in special relativity. We can do that in Newtonian theory. We can use any reference frames we like anywhere. We can use any coordinate systems we want. We have to make adjustments to account for what a coordinate system we're using. But that's an empty comment. It's not a physical comment. It's that we have the mathematics to deal with any coordinate system, and even better, we have the mathematics to have no coordinate systems. We can do this all in a coordinate-free way. I began this saying, don't get confused between physical effects and coordinate-dependent descriptions. So this is an empty claim. Then he says something that's just false. If we were to adopt a frame of reference like Tycho's in which the Earth is at rest, then the distant galaxies would seem to be executing circular terms over a year. I put the sick in there because he should have said a day. And in general relativity, the enormous motion would create forces akin to gravitation, would act on the sun and planets and give them the motions of the tectonic theory. That's just gibberish. He thinks that there's no fact in general relativity that whether the Earth is rotating or the galaxies around us are rotating and we're at rest. That makes no sense. Why? Here's a quick thing. If the galaxies around us are rotating, they're doing it every 24 hours. We know how far those are. They'd have to be going faster than the speed of light. General relativity does not allow them to do that. It's not like general relativity says, oh yeah, sure, galaxies go faster than the speed of light and you'll create some gravitational effects on Earth. And they wouldn't anyway. And the solar system doesn't depend on those galaxies. You can just ask general relativity. Suppose there are no distant galaxies. Yeah, not going to make much difference. Not going to make, it's just completely wrong. And the problem is, you might say, this is Steven Weinberg, Nobel Prize winner. How can I be saying this? First thing, I explain why. Second thing, if you want to check whether what I said is true, get Bob Wald on or get Daniel Sudarsky on. Third thing, you can see it just doesn't make any, galaxies can't be doing that. He's a particle physicist. Particle physicists are not really experts in general relativity. They tend to learn a bit of special relativity and then figure, special relativity is good enough. They don't really understand general relativity. And this is an exact. And the same thing, as you know, all the stuff that Susskind talks about, black hole complementarity. If you stand outside a black hole and you watch someone fall in, they seem to fall slower and slower. Yeah, they do. Just chase the light rays. Just trace the light rays and you'll see where the light rays getting into your eyes come from. But so what? I mean, he wants to say things like, oh, from the outside, the person, first of all, never falls in, and second of all, it becomes incredibly hot and burns up at the event horizon or something. But from the point of view of the person falling in, they go right through the event horizon and nothing happens. And when you say those are really contradictory descriptions, oh, that's black hole complementarity. And that's just the end of logic, right? They can't both be true. A person can't both burn up at the event horizon and not burn up at the event horizon. And optical effects in general relativity are not going to make somebody not on fire appear to be on fire, right? So, this is not hard stuff to understand. And that was Feynman's point. If you understand what general relativity is telling you, it's not that hard. Hard to calculate exactly. Not that hard to understand. But you have comments like this that are dead proof of not understanding that theory. And the real problem is so many people are trying to put together general relativity and quantum theory. It's not going to go well if you don't understand general relativity on its own terms. I mean, general relativity may have to change, there may have to be adjustments, whatever. And there are debates about where there are conflicts, who gives way, and so on. But if you don't start with a clear conceptual comprehension of what general relativity says, and you try and put it together with something else, it can't go well. And it doesn't. And, as I say, firewall stuff, black hole complementarity, this stuff of Weinberg's, very homo people, right? Big names. I'm not an expert, but I understand the theory. This is where we started. And I've explained enough of it that anybody paying attention to what I've said can at least see why I'm saying what I'm saying. And if you think I've made a mistake somewhere, okay, that's good, be skeptical. Try and find somebody who really understands the theory, who'll explain to you what I said that was wrong. I mean, that's the reason I get so, I don't think any part of physics has been held up or delayed by people saying the wrong thing about the twins paradox. I mean, we've gone on about how it's not acceleration, it's proper time, and so on. It annoys me that people do that. I don't think that's held anybody up. I don't think it's put any research program on the wrong track. I think any competent physicist, if you ask them, all right, actually calculate what these clocks will do, they will plug in and they'll calculate the proper time and they'll get the right answer. Just as in Feynman's case, when he asked this question about the clocks, the guy did the calculation and got the right answer. Feynman's point is that if you understood the theory, you wouldn't have to do the calculation. Just throw the thing up so that it's in free fall and gets back at the right time. That's got to be the longest, locally longest path. So that's got to click off the most time. The problem is so much theoretical physics that's focused on putting together general relativity and quantum theory can't possibly work if you don't understand general relativity. Because you don't understand what you're changing, you don't understand what you're adjusting, where you're making adjustments. And I think that's been really standing in the way of making progress. Anybody, I'm winding this up with what you would call dessert.
Okay.
Okay. The first piece of dessert, I'm not going to go into a lot, but I am going to show you this article. This is from the Scientific American, March 1993, Black Holes and the Centrifugal Force Paradox. And I just recommend anybody interested in this, just find this article, Marek Artur Abramovitz. It's a very beautiful argument. It's a very beautiful article about what they call optical relativity. So you say, all right, here, and I just want to show you what's going on here. Here we've got a black hole. We've got the event horizon. We all know that. And they're outside the event horizon. You could physically, in principle, build labs, these toroidal labs at different radii, right? You can't go in, but here you're at, I think 1.5, 2, and 3 radii out. You're building these labs, okay? And so the furthest out lab, there's going to be the least, as it were, effect of the gravity, the least curvature effect of the gravity. And as you get closer, you get more and more. In the middle lab, you've built it close enough that if you send a light ray down the center of that torus, the light orbits. Okay, it's going to come back and hit you in the back of the head. And that's just an inertial trajectory, just a geodesic. So what's it going to look like? Well, that's this picture. If you look, even though the lab is a torus, it goes around, if you look, because the light is orbiting in that direction, it's going to look straight. If you're way outside, it's going to look this way. So this is the outside lab. If you look down your lab, here's the black hole. If this was all windows, here's the black hole. The lab is bending around, and it's going to look like it's bending around in the direction of the black hole. But if you go all the way further inside, where the light can't even orbit, so the light, if you send it this way, it gets pulled in. It means this is what you're going to see. You're going to see more of the black hole, and it's going to look to you like the lab is bending the opposite direction than it really is. And you can figure all that out just by tracing the light cones. Now, the interesting thing in this article, and I'll just tell you what it is, people should read it if you're interested, is that if you, in these 3 labs, if you built train tracks that run around like this, and you get in the train, you start running the train forward. There are going to be effects like when you're in a roller coaster, you know, you get pushed up and down or whatever. These effects are going to be different. here, where it looks like the tube is bending this way, the faster you go, the more you'll be, as it were, pulled out of your seat, okay? Here, where it looks straight, you won't be pulled at all. You'll feel like you're going straight. And here, the faster you go, the more you'll be pushed down toward the event horizon, toward the black hole. Just as you'd predict if you just looked. So that's why they call it optical relativity. Just trace the light rays, figure out what's going to get into your eyes, how it's going to look, and your judgments will be correct in some of these cases. Now, the other thing they use here, and I brought this for this purpose, is gyroscopes. So I said our basic things are going to be clocks, light rays, and gyroscopes. Well, remember, we talked about parallel transport. We talked about moving something and not letting it tip, right? So just grab that. And now, just at your leisure, move it around like this. No problem,
Like
right?
this? Yeah.
Okay. Now, give it a shot. Try and move it. What do you find?
I'm finding that it's moving of its own accord a little bit in my hand.
And it's a lot harder to do, right?
Yeah, yeah.
So what a gyroscope does intuitively is it is a physical device that once you set a direction, the faster this is spinning, the more it wants to keep that direction. It's like a physical way of implementing parallel transport. And that's why guidance systems on airplanes use gyroscopes, right? Because they're just in the plane. They don't look out or anything else. You can just tell by how the plane is moving relative to the gyroscope. The gyroscope is essentially doing parallel transport. So one way to get at the geometry from something visible is to look at what the gyroscopes will do, which in this article they do. This is a kind of uncommon thing. People are usually talking about clocks and rods. Rods are really complicated. Gyroscopes are much better. A normal black hole that people usually talk about forms when a star collapses. But the way you do it is the star is not rotating, okay? But real stars do rotate, like the sun rotates. You can watch the sunspots move. And if the star is rotating, then you get what's called a Kerr black hole. And the nice thing about Kerr black holes, if you sort of think about these diagrams, I said, one way to think about a black hole is as you get closer, the light cones tip in, right? Sort of tip in toward it. But if the Kerr black hole is rotating like this, they not only tip in, but they tip along the rotation. So this one will tip forward and this one this way. They sort of tip in, as it were, in the direction of rotation. And this is a diagram from Hawking and Ellis's book, The Large-Scale Structure of Spacetime, where they're showing you the different light cones as they narrow in this diagram and as they tip. And you see, it's a tip here that way, and here it's going that way. It leads to a much more complicated situation. Before you get to the event horizon, there's something called the ergosphere. I can't go through this, but I just want to indicate to people something. And the singularity, you'll notice at the middle is a ring, is normally called a ring singularity. So it's not a point, it's a ring. And I just want to, again, so people understand how difficult this topic is. Within the last 2 years, there have been complaints about claiming there's actually a singularity there. Complaints among them, people like Kerr. Because if you think a singularity is where something strange happens in space-time, right? Where some density gets infinite or curvature gets infinite or something. And what Kerr points out is that what was really proven is just that there are trajectories of finite proper time, of inertial trajectories, geodesics of finite proper time. Now we saw our Zenonian observer has only finite proper time. He's not inertial, of course, he's constantly being pushed. But what Kerr points out is that that doesn't show that anything goes infinite, that any curvature goes infinite or anything else. And that these results that were proven originally by Hawking and Penrose, I mean, they're good results, but they were reported in a way of singularity theorems or showing the breakdown of space-time. There's even, to this day, dispute about that. I mean, I'm not coming down on it, but there's dispute about that. Now, if you take this tipping far enough, you get Gödel space-time. So you like dessert. This was a birthday present Gödel wrote to Einstein.
Actually?
Yeah. I mean, he did it for the Schulp volume, the same volume that it was like a present to Einstein. He figured out there was a funny solution to Einstein's field equations that he found, Gödel space-time. Intuitively, remember we said in Kerr, these light cones are tipping like this, right? If you keep tipping them far enough, you get a point where staying within the light cones, you can go all the way around. And you get closed time-like curves. You get time travel. You wanted to worry about time travel. You have closed time-like curves here, and you can read them off of this diagram. If anybody's interested, you can go to Hawking and Ellis. And there's a little mistake in this diagram. But anyway, you can see here, you're looking at these circles, and you see once this tips far enough here, this circle is always threading the light cone. Now, that's not a geodesic. To travel along that curve, you would need a lot of energy. It's a very accelerated path. And David Malamud, who you may have heard of, one of the earliest things he did was he calculated how much rocket fuel you would need to do that, to go on a closed time-like curve in Gödel space-time. And he discovered it so much it would destroy the solution. There would be so much mass for the fuel that the solution would no longer be any good.
That's funny.
So as a practical matter, it can't be done. Anyway, there's a lot to say, but it's an interesting mathematical solution. I don't think it's physical. I think it's just an interesting mathematical curiosity. Here's something else that can happen in general relativity. And it's exactly, remember, we started out by Einstein saying, physics is going, the progress of physics is more and more local. The objects, the fields become more and more local, and the laws themselves become local. So you can check whether a model satisfied the laws by just checking piece by piece. Is it satisfied here? Is it satisfied here? Is it satisfied here? That means that in general relativity, there's very little constraint. Essentially, you can put no constraint on the global topology. So here's what I mean. I just want to show you this, and then I'm done. So here's Minkowski spacetime. Remember, this is flat. Future light cone, past light cone. Okay, here's something you can do that will still give you a nice flat spacetime. You can roll it up this way. Okay, paste it together. Now you have it's a flat space-time. It has only finite space. It's not infinite anymore, right? It's compactified. That's fine. That's something that can happen according to general relativity. Why? Because I didn't put any constraints. Anything, if the local stuff was okay, when I do this, it's okay. Here's another thing I can do. Kind of funny. I can roll it up this way. Same thing, just glue it together. That's a solution to the equations of general relativity. That has closed time-like curves, because by going always to the future into the blue, I come right around back to where I started. So I can get that kind of time travel in general relativity just by, as it were, putting it in by hand, because the theory doesn't really constrain the global topology. Now, my opinion is that this is not physically possible, that time itself doesn't allow it. The math does, because we didn't put any constraints on the math. We're letting the math do weird stuff. But here you have to make a decision. If you think this is a serious physical possibility, then you're in a whole different world. I personally think it isn't. That's when Hawking and Ellis wrote their book. They were basically, the idea is that no physically realistic, no physically serious spacetime had closed time-like curves. And the very last thing I want to do is point out that if you don't put any constraints at all, things get even screwier. So here's a little slice of Minkowski spacetime. okay? Blue, future light cone, red, past light cone. Here's something I can do. Our old friend Mobius.
Yeah.
I can put a half twist. Okay. Again, if I'm just checking piece by piece, I'm not going to find anything wrong. But notice now, this is not even temporally orientable. Now I can't even make a clean distinction between the future and the past, directions. Because an arrow pointing into the blue to the future, I carry it around and it comes back then pointing the other way.
Yeah.
So this is an example of a non-temporally orientable space-time. No physicist takes this seriously. I mean, I know of no physicist ever who thought space-time could be like this, that there's not even a clean distinction between the past and the future light cones. In that sense, there's no direction of time at all. There can't be. Okay? So the reason why I wanted to end with these is that there's the mathematics. You write down some equations. And then there's the physics. The equations are supposed to be representing the physics. But you have to think about whether your equations have really captured all there is to the physical reality. If you think that there's a direction of time of any kind, it doesn't even if it's emergent or whatever, but in this non-temporally orientable case, you just can't have one because because it's got the half twist in it. You can't cleanly divide them into the light cones into the two groups anymore. You know, if you think that's physically possible, you've got to go through all kinds of hoops to understand how that could happen or what would happen if it did happen. But the other thing is to say, no, that can't happen. It's just, the mathematical models exist, sure. They don't represent physical possibilities. And if you say, well, how do I constrain them? Easy. You say words like, demand that the space-time be temporally orientable. Then you get rid of this. You don't get rid of it mathematically, you get rid of it physically. Or say, there can be no closed time-like curves. Easy thing to say. And then a whole bunch of models that have them go out the window. Not as mathematical models, but as physical possibilities. So people tend, like Gödel went way over the edge, right? I mean, the reason I'm bringing this up is that Gödel, in my opinion, went way over the edge. He discovered a kind of cute solution to the Einstein field equations. It's cute, it's also really weird. He tried to conclude, if you read his little paper, it's in the same Schulp volume of Albert Einstein, philosopher, scientist. He tried to conclude that this proves that time is unreal. And you went, no. It's just a funny mathematical solution to some equations. We don't have any concrete reason to believe space-time could be like this. You can't, by the way, this you cannot form by a collapsing star or anything else. It can't be formed, which shouldn't surprise you because in a way, if it's got closed time-like curves, you don't even know what you mean by being formed because everything's going around in a circle. So the math is hard. The solutions to the equations, there are lots of them, and you can find weird ones. Where you let the mathematics take over without the physical concepts under control, you're going to get into a mess. You're going to end up with too much math that doesn't correspond to any possible physics. And you can get lost in that. And the solution is to always keep a very clear understanding conceptually of what you're doing and what the mathematics is supposed to be representing. Because if you just allow yourself to devolve into pure calculation, you end up in a mess. And that is the last thing I wanted to say.
Well, Tim, I don't know where to begin or to end rather, but the amount of time and preparation you put into this is just amazing. I think with David maybe now you've surpassed David as the guest with the most appearances on the show. So as ever, and this time especially, thank you so much for being a part of the show.
Thank you. I mean, I know I've annoyed the hell out of you by telling you it wasn't going to be this long, and I was wrong. I apologize. My hope is that because it's recorded, people can consume it at whatever rate they find convenient and go back over stuff. There is a lot of, I'm trying to give you enough real, actual content. Don't take my word for it. But first of all, try to think it through.
One thing, though, that I should ask before we end is what's going on with the John Bell Institute?
Well, thank you for asking. And the answer is, I think the same as the last time I told you, with a slight emendation. I don't really know, but I think I'm going to talk to people in March, in another month and a half, at the University of Split, who may be able to help us figure a way forward. So there's certainly no resolution to trying to find a permanent location. But it's not, we're not just groping in the dark. And so it's slow progress, and we'll see.
People are interested in helping out with the John Bell Institute for the Foundations of Physics. Where should they
Well,
be?
I set up this GoFundMe when I thought I knew what we were trying to buy, which was a place where I set up a lecture room and a breakfast room and dinner. I think I told you last time that the local restaurant we were going to use went out of business, so they stopped serving dinners. And so the logistics is impossible there. The end game, again, is to find some stable location that at least can be used during the summers to put on workshops and summer schools, and ideally for people just to hang out and work on their stuff and talk to other people. That was my vision. I thought I had a place to do it. I don't have. Whatever we do, well, we've got to shut down what we've got and try and recover as much of the material that got put into it and store it somewhere. And then find a location, hopefully, where we can do this. And if we do that, we will still need resources, but I can't begin to calculate or even suggest what they would be because I don't know what the options are going to be. So at the moment, there will be, we've raised some money and it's been very helpful, and it will be helpful trying to move as much as we can of what got put into that location somewhere where we can reuse it and store it and things like that. But how it's going to go, I don't know.
Yeah, well, I'll be watching, I guess. And thanks again, Tim. This is great.
Thank you.